Hi, everybody. Thank you all for coming out tonight. This is the last of our AI lecture series, but if I understand correctly, next Wednesday evening, we're going to have the open data... Say it again? Data Science Conference. Okay, so kind of keep that in mind. Now, tonight we're going to have a number of speakers. First up, we're going to have Tom. Tom is one of the members here at Hacker Dojo. And Tom's industry, or Tom's business, is called 21st Geo. 21 Geo. And 21 Geo is the difference, is the 21st century of gear linkage, whereas the past involves discrete, I'm messing up this explanation, discrete gear linkage, and his is continuous. But anyways, as I bring Tom up here, just want to ask him a few questions. Tom, how long have you been with Hacker Dojo, and what's the best thing you like about it? And I'll go ahead and let Tom take over from here.
I've been a Hacker Dojo member on and off for 5 years. And so obviously I'm very much like the 3D printer. That's a nice thing in the makerspace. But the other thing I do like about it, I'm an MIT grad twice over, and I always appreciated having a lot of technical people around me, people who are actually solving problems. And so when I come here, there's the same sort of thing. You know, in Silicon Valley, once you get out of college, you give up all your problem solving for PowerPoint. Then this is a lot more fun because people are actually solving problems here. Okay. To correct what was said is, we're going to talk about geometry and mechanisms in a moment. And what's in the past for geometry is discrete geometry, which would be linkages. And there's only so much you can do with them. What we're going to see is that I'm offering 21st century geometry, which is continuous geometry. Okay. Clicker, there it is, And I think it's this one. So we're going to start out by talking about some static technology. And this is stuff that hasn't changed. And so static technology, I've never known, what? Technology is supposed to be moving forward, it's supposed to be changing all the time. How is it we're having static technology? And what specifically am I talking about? I'm talking about mechanisms. So the mainstays for mechanisms are gears, cams, multi-bar linkages, and bearings. And all of that stuff has been the same for hundreds of years. To the far left is a drawing of a ball bearing by Leonardo da Vinci. Okay, nothing's changed, nothing's moved at all whatsoever. And using old stuff is fine if you get a good outcome, but we don't. So in an automobile, 20% of the energy that goes into the drivetrain is lost due to friction and other losses. Every time the exhaust valve opens in your car, bang! You just lost half the energy that was in that cylinder. You just gave up on it. Compressors in HVAC and refrigeration are also very, very inefficient, depending upon where you are, whether it's here or Brazil. There's a lot of energy lost there, and 40% of worldwide energy goes into compressors. So these numbers are huge. Now, for instance, if you engine guys out there will know about the Atkinson engine, this is adding linkages to the crankcase of a car to try to harvest more of that energy. The patents for the Atkinson engine are over 100 years old. We can go on the web today and there'll be 3 or 4 projects doing pretty much the same thing, trying to add some linkages to an engine to harvest that energy. And there's dozens of other projects that have done it in the past. So these tools have not served us well. And so what I'm introducing here is a brand new paradigm, something that we can get more out of these systems. So what do I have? Okay, it's the universal bearing technology, and it generates motion specialized bearings. So we're looking at 3 of them together that are creating a device. A couple key characteristics of this. First of all, the pins that you're seeing there roll perfectly. There is no sliding. That's a big part of the engineering. Secondly, the surfaces are also designed so that the contact points on the pins oppose each other throughout the range of motion. That keeps it from jamming. So this is okay. So let me go through and talk about how we actually make this. So what we do is we start with a description of motion, and it's planar, so that's up, down, left, right, and rotation. Now, this is where you get all of what it really is important about this is more flexibility than any other type of mechanical device. Being able to do anything you want, that's what's going to make the difference, and that's what's going to make this an important device. Okay, so we take a description of motion. I need two of them because there's two components, and the bearing sits between them. And then we have a methodology, and that methodology creates a motion-specialized bearing. And that bearing supports the motion that was decided above. Okay, let's walk through a bunch of interesting devices. This is a speed reducer. It is very low loss. It's high torque. It's zero backlash. This is very much in demand this is 105 to 1. This is very much demand in robotics today. Right now, you can't get this combination of features in any other device. Okay. This is a high-efficiency compressor. This replaces the crankcase for a compressor. And what's going on here is this is the intake, quick compression, and then it has 180 degrees of steady injection. And where you lose energy in a compressor is because you inject it into the high-pressure system uneven. If you push too hard, that creates pressure. Pressure becomes force. Force times distance is energy, and you lose that energy. This has 180 degrees of steady injection. And since it's 180 degrees, you only need 2 cylinders. So what currently is being done to get high-efficiency devices is that you use more and more cylinders. That's expensive. So net of it is not only is this more efficient, it is a lower upfront cost. This is what I call a 180-degree engine. So this replaces the crankcase in your car, and it certainly kind of walked through the 4 different strokes. It does all 4 strokes in 101 shaft revolution. So that's the power stroke right there. Exhaust, intake, compression. Power, exhaust, intake, compression. So this is an Atkinson-like cycle, and I say that because you can see that the compression and the expansion cycles are different sizes, that it goes up and down to separate amounts. That's what the Atkinson that's what the Atkinson engine does with linkages. Secondly is I've reserved 180 degrees for the expansion cycle. So that means that I can do 2 cylinders instead of 4, 6, 8, 12, whatever you want to do. So then again, this is becoming cheaper. Lastly, I can program in the mechanical advantage to this device so that we get a constant torque output. So a key part of that is because it's constant torque output on 2 cylinders, I'm getting the smoothness of a V8 on 2 cylinders. Okay, and the last one's for fun. This is a corkscrew. And it's a better corkscrew, mostly because I have programmed into it the way I think it should work, which is you'll see the cork is moving slower at the bottom than it does at the top, even though the lever arm is moving at a steady speed. And what that does is most of the forces when you're trying to get it started, and since it's moving slower, you get a higher mechanical advantage. It's a variable mechanical advantage system. Now, one of the questions, one of the key features of this is that if you look at it carefully, it's standard shape. So you could stamp everything here, or you could cut it, And then the guides system there could be made through molding. So it's essentially molded parts over standard shapes. Okay? Questions?
I know that a lot of robotics requires a lot of microcontrol,
Mm-hmm.
you know, and I'm wondering if that type of gear system is better for that, or is that one of the advantages, or?
So the question is how does this compare in the robotics market and why? So why don't we back up a couple slides and we take a look at it. So I went to a robot show and talked to a bunch of salespeople who have put me in touch with a bunch of CTOs of robotics companies. And what I'm finding out is this is actually a very interesting set of features here. The big problem with robotics and gearing something down is that if this is a gear, two gears interacting, if it's pushing this way, and then all of a sudden it pushes the other way, which is what a robot would have to do, there's this movement back and forth, and that's known as backlash. And if you're trying to hit a precision point, you can't have that backlash because that's all uncertainty. So you need a zero backlash design. Because this is low friction, I can put stress into the system and ensure that that there is no backlash here. So secondly is the devices being used today use a lot of energy, and this is all of these surfaces are designed to roll. They're also more robust than what's being done. Those pins are actually much more robust than a gear tooth. Okay, so those are the kind of key features.
Hey, one other little question. I know you have that little prototype there.
Oh, thank you.
And how did you get that made?
This is made on the printer back there. So this was my trying to figure out how to get it through. So this and that are kind of cousins to each other. They're really the same thing in many ways. It's just that this has 4 pins, and this one on the front side has 14, and the back side 15. And it's that difference between 14 and 15 that give it the 105 speed reduction. So, I'm going to have to leave quickly, but if anyone wants to kind of take a look at this, that's fine. But you can see that it nicely rolls. It's kind of, what do they call them, spinners? It's my spinner. It's my fidget spinner. Okay. Next question. Yeah.
That's good.
Okay.
All right.
Thank you.
Fantastic. I hope everyone found that interesting. Let's see now. Up next is we're going to have V.S. Joshi, and V.S. Joshi is the person who essentially gathers up all of our speakers and convinces them to come here. And so we're going to give V.S. Joshi a little bit of time. He usually does something about the history of AI. I'm not exactly sure what he's going to do now, but I'll just let him take over. There you go, V.S.
Thank you very much. Okay. Okay. Hi, everybody. My name is V.S. Joshi. I am one of the Hacker Dojo members and one of the organizers for this AI lecture series. And I'm still stuck. Okay, there you go. Okay. Again, this is our last lecture of the series. But if in case you are here for the first time, don't worry, because each and every lecture is supposed to be an independent lecture. You don't need to know anything that happened in the 9 previous lectures to understand what is going to happen today. So just don't worry about that. Anybody who's new to Hacker Dojo or here for the very first time? Okay, so I see some 7, 8 hands go up. Okay, so just very quickly, I would just introduce what Hacker Dojo is. So Hacker Dojo has been in existence since 2009. This is our 3rd location. And Hacker Dojo is many things to many people. It is a co-working space. If you come here during daytime, you will see a lot of tables and chairs around the table. And every table is kind of a startup by itself. So generally what happens is whenever the team goes above 5 or 6 people, they graduate from Hacker Dojo and they go somewhere else. They buy a new office and things like that. But until then, people come over here, they, entrepreneurs, wannabe entrepreneurs, two founders debating certain ideas and things like that. They all come over here, they debate their ideas, and they use this as a co-working space. So it's not only for entrepreneurs and wannabe entrepreneurs, but there are many people who use this place as a remote office. They have their corporate office in New York and Washington, D.C., wherever it is, but they use this place as a corporate office. So in total, we have about 300 members or so, and out of 300 members, 100 members don't even come over here. They just like this whole feeling of a technology community that is, that is inspiring new ideas, taking innovative ideas and building their ideas into businesses and ventures and things like that. They just like the feeling of supporting this kind of a community. So that's the reason why they are members. So yeah, so we are about 300 members or so. In addition to that, okay, let me say something more about the startups from here. We have something like 2,500 to 3,000 startups have passed through the doors of Hacker Dojo. And some of the startups you might have heard are startups like Pinterest, Pebble. These startups started over here when there were 1 or 2 people startup. They were right over here. And yeah, so I think we have more than 2,500 or so startups that have gone through here. In addition to that, it's also a maker space. On the corner over there, you will see some 3D printers. There is also a soldering gun. There is also a laser cutting machine over here in the corner room over there. Plus, it's also an event space. I think Jim was mentioning something about the open data science event that is happening next Wednesday. But every day, some or the other event is happening. Like today, there was some Intel event that was happening over here. A lot of hackathons happen over here. Lightning talks happen over here. Coding camps happen over here. Not only the coding camps, there are kids technical education camps, and all those things happen over here. So it's also a big event space. We have had something like 5,000 events that have happened over here. And if you are a member, of at Hacker Dojo, you can book one of these rooms for your event, and that's not a problem at all. Yeah. So think of becoming a member. You can just with one event, your fees will be completely taken care of, because our fees are something like nominal fees of $125 per month, and you have 24/7 coffee. Sometimes people who make coffee, they are not good coffee makers like me, and then you'll have to suffer through that coffee. But otherwise, if you're good at making coffee, then okay, it's wonderful coffee over here. And it's also a learning space. So this AI lecture series is a part of that learning space experience. We started this AI lecture series. Again, we don't charge anything to anybody, and nor do the speakers try. I mean, Jim, you said, okay, I got the speakers. It was convincing them. Believe me, it was no convincing them. They were all eager, and they were all with a noble thought of demystifying and democratizing AI. They are all over here. That's how our speaker is today. He's also here for the same reason, yeah? Okay, so before I get into this topic, I just wanted to find out if there is somebody in the audience who would like to make a 30-second, 1-minute announcement, introduce themselves, make an announcement or something like that. Okay, Murli, I get you. Anybody else? Okay, Andrea, yeah. Okay, Karthik, is Karthik? Okay, cool. So why don't we start with Murli here? Murli, why don't you start, and then Andrea, you can come over here. Karthik is over there. Come on this side.
I like to go by my middle name, Krishna. It's easier to pronounce as well. I used to be a member. I still hang out here a lot. I've been attending these talks, and it was an idea that had been nagging in my head for years. And I think I have an idea about how to use something I learned here to solve this problem. And I like to call it, the solution I have in mind, I call it credibility score. Everybody knows what's a credit score. And you have a credit history, the whole report, and then there's a score that quantifies your creditworthiness. Similarly, credibility score is like, okay, so there are people giving talks here. There's one dimension is how much do they know, right? What's their competence level on the topic? So my competence level is maybe 5%, 3% on most of these topics. So I measure this in the reverse way. We are all incompetent at topics we don't know. So 100% incompetence, and you want to remove the incompetence by knowledge, up to 0%, right? So somebody who's very knowledgeable about a topic. So the credibility score, one dimension is that. But there's another aspect. Anybody want to guess what that is? Yes? No, but like if we are measuring somebody's credibility, the other dimension is honesty, right? Somebody can be very knowledgeable but completely dishonest, especially in politics and so many other areas, right? Real estate, used car dealers, and so on. So you want to know what is the dishonesty level on a scale of 100 to 0. So combining these two, I want to create a similar score, and there's a lot around it. I've discussed with the person who gave a talk on NLP, natural language processing. This has to do with reading comprehension, and it's quite doable. I'm looking for people who are interested in working with me on this. My contact information is just go to 4weekstartup.guru. I'm not pitching my idea, but URL, but that's an easy way to remember me. Otherwise, I'm right here, just come talk to me. Thank you.
So Murli, as you got your inspiration from Hacker Dojo AI lecture series, all the speakers, 100 credibility level here, okay? Please, yes. Andrea, yeah?
It's going to be short. Hi, everybody. My name is Andrea Amaraji, and I am the founder and principal of a consulting practice called Cohere Insights, and I specialize in analytic strategy and technical implementation of the strategy. Anyone here work in analytics programs? Do any kind of analytics, data analytics? Have you ever been part of a program that didn't quite go so well or deliver business value? Yes. Hopefully is the answer yes. I've been involved in a lot of those programs, and I have culled my experience into my practice. Next Wednesday, I'm going to be giving a speech at WePay. Next Wednesday, November 14th, that coincides with the event here, but if you're up on the peninsula, it's going to be at WePay in Redwood City. It's hosted by the meetup called Project Management AI, Silicon Valley Project Management AI, but we're focusing on analytics. I'm doing a slight machine learning bent to it, but we're going to be talking about strategy and how strategy helps analytics deliver value for the business.
Okay, any last two speakers? Okay, Karthik?
Good evening, everyone. My name is Karthik Gada, and I do two different things. One is investment banking, M&A for artificial intelligence companies. So if you are an AI company that is, let's say, post-Series A or at least close to that, and you have some revenue and you want to get sold, by the big, and be bought by the 20 or 30 big companies that acquire all the AI companies, please come see me. I'm one of the only investment bankers specialized in AI, and I write my own research reports as well. Another thing I do is I do a lot of keynotes about artificial intelligence, and I've written a book about the real economic impact of that, and I teach a class at Stanford about it as well, which is open to everyone, Business 237 if you've gone to Stanford continuing studies. Because I'm always invited to talk about what will happen with AI and jobs, for example, and I find that debate to be very limiting, so a couple of key insights I want to share with you, which nobody else is thinking about in this debate. If we are to believe that AI is taking away jobs, as well as something like blockchain is making security and other processes faster, then you must necessarily believe that, well, AI could automate a lot of government jobs and a lot of government functions as well, right? Government services should cost 1/10 or 1/100th of what they cost now. Why did the DMV sticker cost $300, whereas iTunes only $1.39 per song, or YouTube is free, Netflix is $8 a month? That saving could be passed to the taxpayer, because when we say AI is taking away jobs, well, the human is taxed, AI is not. That's not fair. You're fighting with one arm behind your back, right? 50% tax rate. So that is one thing entrepreneurs should think about, because most startups are trying to disrupt a $2 to $3 billion market. Why not disrupt the $25 trillion market, right? Which has the lowest productivity, and you can't have the private sector becoming more and more productive and the government less and less. That gap is untenable. So that is the greatest technological disruption of our age. It's already happening, but in fits and starts. And startups that do that and partner with small countries to say standardize certain things because big countries aren't going to do that will come out ahead. The second thing that's extremely important when you think about AI and jobs is the personalization of education. This whole notion of job obsolescence, long-term unemployment, and all that, it's a training issue. It's a training timeline issue. Now, AI is doing a lot to personalize education. A couple of my clients are big e-learning companies using AI. If you can increase your rate of learning by 25%, 50%, which is possible under an AI learning model, because the classroom model is an extremely blunt instrument, bluntest of blunt instruments, which is just what we're used to, then that really solved the whole issue because you can retrain very quickly. You can stay ahead of AI. The same AI that's automating certain jobs is also ideally fostering faster training and retraining and so forth. And that's something I want you to think about as well. The book that I've written is available free online. If you look up my name, Kartik Gada, it's on my LinkedIn, Facebook, everything, 450,000 views about this subject, and it's been a Google Talk as well. Thank you very much.
Yeah, we have one more person. Hi. Oh, newest member. Okay, wonderful. Welcome.
Wow, you guys are tall, huh? Hi, my name is Yiğit. I am from Turkey, and I arrived here 3 months ago, and I came here just today just to check it out and see what it's like. And so far, I've been really impressed with the energy in here, and I'm really looking forward to contributing to projects and implementing mine as well. I'm a mechanical engineer. I'm a product designer as well, and now I'm getting my training to be a project manager. So if you guys need any help or if you want to contribute to my work, I'm always open to suggestions and open to connections. Thank you.
Wonderful. You said you're a chemical engineer, right? Yeah. Okay, cool, no problem. Thank you very much. So anyway, folks, the reason why I chose, let me dive into this AI at the edge topic. The agenda is, okay, I will speak a little bit of AI at the edge, and then we will have the main speaker come over here and talk about autonomous vehicles. So, I think this was a warm-up act for the main speaker for the simple reason that he's going to talk about autonomous vehicles. And when you talk about autonomous vehicles, there's a lot of AI that is happening at the edge, and your car, your vehicle being the edge, yeah? So that is the reason why I'm going to talk a little bit of AI. So I think the way I'm going to kind of talk about this thing is, again, there are many people who are new. So very, very quickly, just going to go through a couple of definitions. What is AI? What is machine learning? What exactly is AI in the cloud in the very first place? What is AI in the cloud? What are the challenges with AI in the cloud? Okay, then what is AI? What is AI at the edge? Can everything be done at the edge, or do we need to separate some of the tasks in the cloud and some of the tasks in the edge and things like that? And give you a couple of examples, and then that will be a lead into Adrien's topic on autonomous vehicles, okay? So just what exactly is artificial intelligence, okay? Again, for people who have been here and coming here for a long time, you can just go off to sleep for the next 3-4 minutes. Essentially, AI is a set of technologies that enable machines, computers to perceive, think, and act. So there are the 3 operative words: to perceive, think, and act, and to solve problems just the way we human beings do. Again, it is a set of technologies. And as I said, the 3 operative words are that enable the computers and machine to perceive, think, and act, okay? When you talk about perception, we're talking about things like computer vision and natural language processing. That's how we perceive things, right? We see certain things, we hear certain things, and that's what perception is, yeah? Computer vision, in the case of machine, it is computer vision and natural language processing. The thinking part is the machine learning part of it, and action, that is where we have autonomous vehicle, robotics, and virtual assistant, and chatbots. All those things are actions, essentially. So again, so this is a very high-level view of what is AI. AI is a set of technologies that enable computers to perceive, think, and act. And when we talk about perception, we are talking about computer vision, natural language processing. When we are talking about thinking, we are talking about machine learning. And in machine learning, there are different kinds of machine learning, different kinds of models and things like that. Machine learning is the way the machines learn. Yeah? That is what machine learning is, okay? And then you have autonomous vehicles. And today, Adrien is going to talk about autonomous vehicles. We have had lectures where we have had experts coming over here and talking about each and every of those circles that you see. We have had somebody from Microsoft coming and talking about computer vision, somebody from Amazon coming and talking about NLP. And machine learning, we had IBM and Oracle people coming and talking. And today is the final lecture. We are going to talk about autonomous vehicles, okay? So this is the overarching AI thing. Now, then what exactly is machine learning? Machine learning is the science of getting computers to learn. Again, machine learning, it is a science of getting machines to learn. To learn without being explicitly programmed, okay? That is the most important thing to remember. Science of getting computers to learn without being explicitly programmed. And think of a baby. Think of a way the baby learns certain things. You are not programming a baby or anything like that. You keep on telling the baby 100 times, A for apple, and B for boy, and things like that. By providing those continuous data to the baby learns, okay, I got A for apple, and okay, this is a banana, this is an apple, this is a pineapple, and things like that. So that's in the in this particular world, machine learning is the science of letting the computers and machines to learn certain things without being explicitly programmed. And yes, this is one slide that an image that I saw on the internet. I don't know what the source is, so I have written here, source of the graphic is unknown, but this is one of the very good slides that I saw. And this is talks about machine learning, what are the different kinds of machine learning. There's a supervised machine learning, unsupervised machine learning, reinforcement learning, and again, within those supervised learning, you have this various different models or something like that. So just keep that thing in mind. I'm just trying to, there is a lot of confusion, a lot of words are thrown at us, and I'm just trying to separate all these things, trying to make it a bit easier for us to understand and to appreciate these things. So again, these are the various kinds of machine learning. And what happens in supervised learning? In supervised learning, the data is fed to the machine, okay? In supervised learning, data is fed to the machine, and the data is a labeled data. So think about it, that yes, you are shown an image, and you are told what that image is. And that is the kind of data that is fed to the machine. And this is just the training of the machine that is happening over here. The machine is being trained, just the way a kid is being trained by showing him, okay, this is a banana, this is an apple, and things like that. Similarly, a machine is being trained, yeah? So let's say, for example, you have to train a machine on bananas, okay? So you show the machine through computer vision, through pictures and things like that, you show the machine 1,000, by the way, there are 1,000 categories of banana. I mean, I was just doing some research in the morning, and I realized there are 1,000 categories of bananas. I had no idea about that. But then you feed that information to the machine. These are the thousands and thousands of bananas, and these are the pineapples, and there's the apples, and things like that. That is just the training part. The machine has not done anything for you as yet. You have merely trained the machine. That's all that you have done so far, okay? Now, when you get a new input data, let's say, for example, the new input data is a basket of fruits, yeah? Then the machine figuring it out by itself, oh, okay, these things are bananas, these things are pineapples, these things are apples. Now that is where the machine has done the inferencing part of it. This part was the training part. And that was the inferencing part where the machine realized, okay, the moment these things were presented, the machine realized, okay, these are bananas, these are pineapples, and these are apples, and things like that, yeah? So this is the inferencing part of it. So again, what I'm trying to say here is, when it comes to machine learning, there are these 7 steps to do machine learning, okay? The first thing is, you have to gather the data. You have to gather the data, you have to prepare the data, you have to choose a model, the model that we saw in that machine learning chart that I saw from an unknown source. You have to choose a particular model. You have to choose that model. You have to train that model. And the difference between training and evaluating is like this. Let's say, for example, you have 1,000 images of bananas, okay? You have 1,000 images. So you don't feed all the 1,000 images. Again, you have 1,000 images of bananas that are labeled. Somebody has written, yes, this is a banana. Yes, this is a banana, okay? And this is a pineapple. So there is a label here. Huh? So when you are training, and let's say you have 1,000 images, you feed the machine only 700 to 800 images. You keep the 300 images on the side, okay? Now, once you have chosen the model, you train this particular model with those 700, 800 images. Now the machine understands, yep, I got it. This is a banana, okay? And now the 300 images that you had kept aside, now you start feeding those things. and see whether the machine understands that. Because I know that is a banana. The machine understands that. And yes, slowly the machine will start understanding and things like that. And then you are doing hyper-tuning, by which if the machine has made a small mistake, like in the previous, again, maybe the machine makes a mistake between this picture and this picture. They don't know what exactly it is. So you kind of hyper-tune it, saying, no, this also is an apple. Maybe this is a green apple or whatever it is, yeah? So you kind of do that hyper-tuning. And so these are the various steps of machine learning. So now, I just want you to look at, and then this is the finally, okay, hold on. This part is the training the model, okay? I just want you to see again. 7 steps of machine learning. The first 6 steps of machine learning are you are essentially training the model, okay? Gathering the data, preparing the data, choosing a model, training the model, evaluating the model, hyper-tuning it, and things like that. Now that the machine is trained, now you have a model, that is, you have a trained model now, okay? You have a trained model, you have a prediction engine, you have an inferencing engine. That's all that you have. And that's your 7th step, predicting or inferencing. Until here, you are training the model. And then finally, the model is ready, and the model is ready to be applied wherever you want it to be applied or wherever you want it to be deployed. And whenever it is deployed, it starts predicting things. Now you can get any, let's say if there is a banana over here, you just show a banana to that. That machine has not seen that particular fruit, but that machine understands that. So that is that inferencing or the predicting of the banana, okay? So these are the 7 steps of machine learning. And now what happens is, these 7 steps of machine learning, when it happens in the cloud, okay? When these are essentially API-driven ML services. So if you are an application vendor, if you are a developer, you don't need to train the machine. And let's say, for example, you have an app which essentially, let's say, for example, you take a picture of a pet. And half the time, I don't know what pet that is or what kind of a dog it is, whether it's a German Shepherd, whether it is a Golden Retriever, whether it is a poodle or whatever it is. I never had any pet, so I don't know what it is, right? So if I take a picture of a pet, right, and then that image is sent to the cloud, and yes, somebody has already trained the model that, yes, this particular is a Golden Retriever from maybe some XYZ country and things like that, and that information is sent back to me. So now that is an AI and machine learning that is there in the cloud. I take a picture, I send the image to the cloud, and then from the cloud, I get the information that, yes, this is a Golden Retriever or whatever it is, right? So that is that, and again, that happens because of this APIs that go from my application to the cloud service that I'm providing. Again, so now you have data from vast IoT devices. It gets transmitted to the cloud, it gets stored there, it gets analyzed there, and then it provides you some certain insights or certain actions that you can do, So that's basically the cloud model of machine learning. And you have companies like Amazon, AWS, Google, Google Computer Engine, Microsoft Azure. They're providing these cloud services. So essentially what they're providing you is they are providing you these APIs by which you can connect your app to these cloud services through APIs, and you can get that information from these various machine learning services providers. Yeah, I'm just showing this as an example. This is Google Cloud's AI building block, right? So if in case you go on Google's site, this is what they show. Okay, you can get cloud vision APIs, you can get cloud video intelligence APIs. In languages, you can get the natural language APIs and things like that. So what happens in a cloud vision API is, yes, again, you want to find out whether this pet is a dog or a cat or what kind of a dog and things like that. You get this service from Google, Cloud Vision API. You get this service from Google, and the moment you take an image, it goes up and it comes down. Now, that is one call that you have made to the service, right? And this is the way the servicing works, 1 to 1,000 units per month, it is free. So let's say you take 1,000 pictures of, you have an application and you take 1,000 pictures of the pets, and it keeps on giving you the right answer. For the first 1,000 images, it is completely free. After that, they charge $1.50 for up to 5,000 images. And then afterward, it is like $1 after that, from 5,000 to 20 million, I guess. Oh, sorry, 5 million, sorry, okay. So 5 million units per month, okay? So if you are having an app which people are using it, and they are sending 5 million images to Google Cloud, Google Cloud is charging only $1.50? Is that what it means? Per? Okay, price per 1,000 unit. Okay, yes, it is on the top. It is yes, price per 1,000 units by monthly usage. Okay. So, okay, so if I am sending 5,000 images, then I am spending $7.50. If I am sending 5,000 images, and the price is 1,000 units, price is $1.50 for 1,000 units, right? So yeah, $7.50. That is the amount of Google charges. So this is AI in the cloud. Google is doing all that kind of work. Similar service is being provided by AWS, similarly provided by Microsoft Azure. So this is for the vision part of it. And then there is always also the natural language processing part of it, wherein you kind of send, say, a statement, and then it will figure out, okay, this is the entity, this is the event, this is the main speaker, it will find out those kind of things. So again, just giving an example. Now this is for a model that is already trained, okay? What happens if in case, let's say, for example, you want to find out what kind of a handbag it is, or something like that. Now, in that case, you have to train that model. You have to send this model thousands of images of handbags, by which they will understand, yes, this is a handbag, yes, this is this kind of a handbag. So when that is required, then what is required is the training part of it. And for training, as you can see, Google has a different charge. You are now training the model, because yes, your requirement is a very specialized requirement. You want to find out about the handbags. Yes, cats, dogs, bananas, apples, pineapples, Google can take care of it. But now you have a specialized requirement of handbags. Okay, now you need to train the model. So now we have two parts. One is training the model, and then there is a charge for that, and then there is a charge for predicting after you use that particular model. There is a charge for the prediction part of it, yeah? So this was the cloud. This is AI in the cloud, right? But then what are the challenges with AI in the cloud? These are the challenges. Privacy, right? Imagine that you are having some camera in, again, the camera is monitoring baby activities and things like that. Now that information is going to the cloud. People are not comfortable with that. Or for example, you have some kind of for senior citizens in their bathroom and things like that, you have certain devices, or you have certain way by which you want to take care of it, that okay, if in case they are stuck in the bathroom, there has to be a way for somebody to help them. Now that information needs to be sent. Again, people are not comfortable with that. Again, that is a privacy issue. Then there is also the latency issue, you know. We cannot make real-time decisions. Right? Imagine there is no internet connection at XYZ thing, okay? It goes there and you're waiting over there. Imagine autonomous vehicles, yeah? You send information to the cloud and now you're waiting, and by that time you will go and hit a tree, you know, because you're waiting for information from the cloud. So that being the case, you have to be, these are the issues, challenges with the cloud model, okay? And again, I just want to show you one video clip, which is essentially talks about the challenges that are there at the edge. And if somebody is waiting for some information from the cloud, there is a huge problem over here, right? So that, again, this is and I'm just trying to set up the scene over here. This is from a movie called Crimson Tide. It's a Gene Hackman, Denzel Washington movie. And in this particular thing, this scene is on a nuclear submarine. And Gene Hackman in this particular thing, he wants to launch the weapon. And Denzel Washington, who is the XO officer, he's saying, we don't have the information as yet. We got one piece of information from the commanding officer, and we'll call, in our terms, it is from the cloud. We got one information, but there is also a second piece of information we got from the cloud, from the commanding officer, and that information is garbled. And because we don't have that, we cannot launch this thing. And he is saying, no, we got the first information, we are going to launch it. And this is this particular scene. Just have a look at it. And again, we will appreciate. What happened? Where is it? Hold on, guys. Just what? Sorry? Where? Please. next series, we are going to fix all these issues.
No, it's not. I don't know. Right.
Rules that are not open to
Aha.
interpretation personally.
Oh, yeah.
That we have backup. Now it's our duty not to launch until we can confirm. You're presuming that we have other submarines out there ready to launch. As captain, I must assume that our submarines could have been taken out by other recruiters. We play these games all night, Mr. Hunter, but I don't have the luxury of your assumptions. Mr. Hunter, we have rules that are not open to interpretation, personal intuition, gut feelings, hairs on the back of your neck, little devils or angels sitting on your shoulders. We're all very well aware of what our orders are and what those orders mean. They come down from our commander-in-chief. They contain no ambiguity. Mr. Hunter, I've made a decision. I'm captain of this boat. Now shut the fuck up! Weapons con. Ship targeting the target package SLBM 64741/2. This is the captain. Captain, I cannot concur. Repeat my command. Sir, we don't know what this message means. Our target package could have changed. You repeat this order or I'll find somebody who will. What do you want, sir? You're relieved of your position. Cobb, remove Mr. Hunter from the control room. Get Lieutenant Zimmer in here right now. No, sir, I do not concur and I do not recognize your authority to relieve me under command of the Navy regulations. Cobb, arrest this man and get him out of here!
Under operating procedures governing the release of nuclear weapons, we cannot launch out missiles unless both you and I agree.
Cobb, what are you waiting for?
Sir, this is expressly why your command must be repeated. It requires my assent. I do not give it. And furthermore, you continue upon this course and insist upon this launch without confirming this message first. I will be
Chief of
able to act by the rules of
Precedent
precedent.
captain was commanding officer of the USS Alabama. I order you.
One of my XL charge the Navy regulations.
I said it there. I order you. What's the command? Under arrest on the charge of mutiny. Huh?
Captain, please, the XO is right. We can't launch unless he concurs.
To the USS Alabama. Rebel-controlled missiles being fueled. Launch codes compromised. Distance. Threaten launch at continental United States. Set DEFCON 2. Immediately launch 10 Trident missile sorties. They're fueling our missiles. We don't have time to fuck around. I don't have to think this over. Captain, I relieve you of your command of this ship.
It's very powerful scene, eh? Okay, so what I'm trying to show here is that, that's good question. Whoa.
Very well. Make your depth 150 feet. 0 bubble. Commence on.
Okay, what we're trying to show here is this is at the edge, right? I mean, they are waiting for commands from the central command office or whatever it is, right? And there is a latency in between what the command is at that has been given by the central office versus what is happening at the edge, that is at the submarine, right? But certain decisions, they have to be taken here at the edge, okay? And yes, you cannot wait for certain things from there. So that is the reason why we need some AI or intelligence at the edge so that you don't have to go through these kind of situations is what we're trying to show you. Okay, now, hold on. Anyway, so I think, again, this is just an example as to, okay, what will happen in a dumb car, okay? I mean, if in case you send the information to the cloud and wait for you to get the information back from the cloud, you will kill at least 2-3 people. Your car will climb on a tree also for that matter, yeah? So again, but in a smart car, a lot of things will happen at the edge itself. Again, I'm just going to run through it because Adrien is going to cover anyway all these things. So again, but then what exactly are the problems with the edge AI? With the edge AI, you don't have that much processing power at the edge. You have limited resources. The battery power is not there. The bandwidth is not there. All these things like the TensorFlow, even though you compress them, still at the edge they cannot be held at the. I mean, there is not enough computing power by which it can be held at the edge. So now again, we talked about training a model and inferencing at the edge. So yes, can we separate these two things? Can the training happen somewhere else, and can the inferencing happen somewhere else? Yeah. What was happening in the cloud AI was training and inferencing, everything was happening in the cloud. But if you keep training and inferencing at the edge, there is a problem of the resources, computing resources and computing power and things like that. So what is happening at the AI at the edge is, okay, can we have some part in the cloud and some part at the edge, yeah? So this is what companies like Microsoft and Qualcomm are doing. This is the Microsoft partnership with Qualcomm where they jointly created a Vision API developer kit. So what basically they're doing is, they're taking the Qualcomm is famous for its chips, chipset and things like that, yeah? So Microsoft is working with their Microsoft Azure and IoT Edge. They're working with Qualcomm, and they're essentially providing a kit to developers by which this AI in the cloud and the inferencing that at the edge, both of those things can be possible for a developer. Because yes, with the chip that is there from Qualcomm, you can, this empowers all the Qualcomm latest AI hardware accelerators to deliver real-time AI. Again, if you look at this thing, oh, sorry. On the top, you will see this no neural hardware accelerator. When there is no neural hardware accelerator, you will see that when it comes to light edge, there is no inferencing happening, there is no training happening at the edge, or in case of a light edge, there is a little bit of inferencing happening, but there is no training. But yes, with this neural hardware accelerator, the hardware accelerator from Qualcomm, which is kind of optimized with Microsoft Azure's ML services, then yes, you have a lot of inferencing and a lot of training happening at the edge, at the light edge and at the, sorry, that's the, yeah, light edge and the, okay. A lot of inferencing and training happening at the edge because of the neural hardware accelerator. So essentially, you are having some specialized hardware to make these things happen. Another example is our own iPhone. Like I have an iPhone, which is essentially an iPhone X, and you have a Face ID mechanism over there in iPhone X. So again, what is happening over there is, we have this flood illuminator. With the flood illuminator, it can detect a face. Even at night, it can detect a face. Then you have the infrared camera. The infrared camera is taking infrared images. And all these, and then you have the dot projector. The dot projector is essentially, pushing the infrared images and the infrared dots to the neural network. And through the neural network, it is creating a mathematical model of your face. Now, if that mathematical model matches with the mathematical model that was created when you did the setup and things like that, then the phone is unlocked, right? So over here, what exactly happened was, iPhone X, it scans the okay. So, okay, I think the way to look at it is this way, that Apple essentially created that neural network by using thousands and billions of images. That's how they created that neural network. Apple also created that A11 bionic chip, and you have now a specialized hardware that is essentially optimized for this neural network, and you have an inbuilt neural engine in that A11 bionic chip, yeah? And that is the way AI is being deployed at the edge, right? So with specialized hardware and things like that, and with that, I think I'm going to introduce you to Adrien. Adrien, he's from Toyota Research Institute, and he's done his PhD. He's a machine learning, he's an expert at machine learning. He has a big team over there. He called me to Toyota office, and I saw his entire team and things like that. Very fancy work that they're doing over there. And again, this is right in Los Altos. It is El Camino, if in case you get a chance. I mean, I pass that road almost every day, and I never realized that there is a big Toyota building over there and the Toyota facilities over there. Again, as you can see, his accomplishments over here. Okay. A lot of awards and patents and publications in computer vision, object detection, and more. And with that, I would like to introduce Adrien. Adrien, please.
All right. I'm the only lucky one that got to stand up, so I think you can, after all this massive information that you just received, you can stand up and stretch a little bit. I think that would be good, because you're ready to be hit by another wave. So just stand up, take a few minutes, relax. I should be, oh yeah, I have to, right. There you go.
Because he didn't go out of full screen.
Oh, sure, thank you. When I was doing that, just factual correction, I have more than 30 papers and patents, just saying. It's off by an order of magnitude. Okay.
I was checking the LinkedIn. So.
All right. So, thank you, everybody. As Via said, I lead the machine learning team at TRI. Yep, sorry. We are a subsidiary that was created by Toyota 2 years ago here in the Valley to work on autonomous driving, robotics, and material science. I guess here in Hacker Dojo, I should say we are a startup that's 2-year-old that got $1 billion in pre-seed funding. Maybe that's more accurate. And yeah, I'm here to talk to you about automated driving and how we are, going from car to robot. It's going to be fairly broad. In the spirit of, the reason I'm doing this here is really just to really try to democratize. You're probably seeing every day some news about autonomous driving, autonomous cars, AI, ad nauseum. I'm going to try to have you peek behind the veil, behind the curtain a little bit. And we're going to go through these simple questions that have complicated answers. And I hope that by the end, you are very confused, but eager to learn more. So we start with why, okay? Always start with why. So why do we care about AD, automated driving? Do you know what this is? Can you guess? Is that a dog? No. You need to train more on images of cities, especially cities from Bulgaria. So this is a city that's called Kula. Has one particularity. It has 3,287 inhabitants. I think in 2013, so it probably has changed a little bit by now. But can anybody guess what 3,287 means and why I remember it well? In relationship to autonomous cars. I'm not going in a complete tangent there. A little bit, but okay. 3,287. That's the number of fatalities on the road per day. So just to put this in context, every day, like today, this town has been nuked, right? Every day. So just 20 to 50 million people getting injured worldwide. It's really, really crazy. So to put this in another perspective, right? It's maybe hard to grasp that there's a small city in Bulgaria that gets wiped out of the map every day, right? This is a 337, right? This is the same basically as saying that every workday of the year, a plane falls out of the sky and people die, okay? So maybe that grounds you the problem a little bit more. And that's real, okay? That's not, Silicon Valley, blah, blah, etc. That's real. That's really real. It's hard to kind of like grasp sometimes, but this is really, really happening. So it's not all that bad, right? I don't want just you to be depressed, and me neither. This is a graph by NHTSA, so NHTSA, so the National Highway Traffic Safety Administration. So you can see here, over 40 years, the traffic fatalities have gone down, right? So we've improved. Just one death is already too many, but it's steadily improving, except if you look actually at 2017 number, the latest number, it's now 37,133 in the US alone, okay, per year, fatalities per year. And that's actually increasing, that has slightly increased in a few recent years. Can you guess why? Ding, ding, exactly, absolutely. And you can see when you're stuck in traffic that people actually do that, right? And we've all been guilty of it to some extent. So that's another graph from NHTSA, the same report from last year. So this is it's going down. It's gone a little bit up recently. Actually, 2017 has gone slightly down compared to 2016 for an increase in vehicle mile travels, like 1 million miles travels. So here, what you see is that, I don't know if I have the laser pointer, yeah. Here you see that it's the death inside the vehicle, so the vehicle occupants, and here below is the death outside the vehicle. And you have this trend that people buy big SUVs and they're safe inside, but they're killing more people outside. And related to that, there's another plot to actually understand this, which is deaths in urban areas, which is this green curve, have now taken over the deaths in rural areas. And so what it means is that we're driving more in more dense, busy urban areas with more pedestrians, more cyclists, more motorcyclists, and the cars are bigger and nastier and they kill more people. Another thing, like without getting too serious about life and death, is some problem that nobody has here in Silicon Valley. So I'm going to explain it to you. This is traffic. So people decide to be one person per car and just take the same exact route every day as everybody else at the exact same time. And these kind of things happen. I know it's hard to, why would people do that, right? We're smarter than this here. And so, yeah, this is horrible, right? So this is 162 lifetimes wasted per year in the US alone, right? Remember that plane that I showed you earlier that falls off the sky and people die every day? Well, if you're lucky and you're not in that plane, then you might be in another plane, this one, which means you're sitting your entire life locked in that plane, no movies, and you can only eat mini pretzels. That's it. 162 lifetimes, it's an entire plane every day, stuck in traffic. Okay, beyond the negative reasons, I can make it a bit, okay, let's leave the sound on. So there are other reasons, right? Not just saving lives, not just avoiding road rage and traffic. There are also simply people that cannot drive, that do not have the choice of mobility. And I'll skip this thing. And actually, a lot of companies, and us included, Toyota, we really, really care about mobility for all. And so this is a campaign that's called Mobility for All. And the goal is really everybody, whether disabilities or any reason, should have access to mobility. There's a reason why we're accepting as a society that a plane falls off the sky, like basically the traffic fatalities, right, is because the freedom we get, right? And so freedom and mobility is really, really important. And so we're going to get access to any kind of people. And you might have seen the Waymo car with blind people in it. There's the Tokyo Olympics in 2020 and the Paralympics, and Toyota is a big sponsor. And we're actually actively working with disabled people to make sure that they also have the same rights as everybody else and the same freedom. Okay. So besides the people with limited mobility, to give mobility for all, so having autonomous cars is important for a blind person, for instance, there's also other reasons why we do automated driving. It's economic opportunities, right? As simple as that. It's going to be a huge revolution. So this is a concept that we introduced at CES called e-pallet. And you've all heard about ride sharing. And autonomous vehicles, and I'll talk a bit about this more in detail, have tremendous economic opportunities in terms of revolutionary transportation, services, deliveries of goods, and there's many, many economic opportunities there. So in the interest of time, I'll skip this, but I think the slides will be shared later, and you can have a look at these videos. So just to summarize what we learned in the first part, which is, I think, really, really important, right? So here it's not so much about democratizing or teaching you new skills or learning some things. It's about why am I here in the first place? Why did I move my family across? I'm French, so I moved my family across the world to come here and to work on this is because we care about AD. It's simply progress, right? It's humanistic values of progress. That's why we're doing it. Saving human lives, improving mobility, and also progress is not just about saving people, it's also making the world, richer, healthier, and so there's a lot of economic opportunities. And I hope I convince you that this is not just BS, we say, to get VC money or whatever. If we do this, it's real, and it's gonna happen, and that's why so many people actually are really motivated by that. All right. that was a bit heavy, and so I'm gonna make some little interludes in between these big questions, these big sessions every time. So XKCD Comics, if you don't know, hilarious. So he has done, Randall Munro has done a lot of ones on driving, so I'm gonna interleave a little bit of that. So it says, it's time to accelerate this giant machine up to terrifying speeds and steer it using my hands, which I'm allowed to do because I took a 20-minute test in high school. Driving freaks me out. Yeah, that's something to think about. All right, after the why, we're gonna talk about the how. How are we going to get there, right? I painted you, the bleak picture of the present and the rosy picture of the future. All right, let's get to work. So of course you're here. It's the AI lecture series, and so AI is the way, all right? And now you can all go home and we're done. So what is AI? So VS explained a little bit what AI is, but as a true computer scientist, now living in the Silicon Valley, I have a methodology to define things, which is I just Google for them. And so if you Google for AI, this is what you get. AI is blue with some plastic garbage looking at some, that's gibberish, all right? Okay, that's also why we're here, is like there's a lot of madness around this. Okay, another type of, if you dig a bit deeper into the science actually, then you say like, all right, AI is about generating images of dogs. And so for those of you that don't know, Jan Goodfellow, which is a really, really awesome research scientist at Google and before was at OpenAI, he has done a paper called Generative Adversarial Nets. I don't know if maybe you've heard about GANs, the acronym, GAN. This paper was published 4 years ago at NIPS. This is one of the major conferences in machine learning, and has 5,000 citations, which is huge. It's insane in that space for like a paper that's 4 years old. That's in the paper. They were learning to generate images. They were learning a neural network on lots of images to generate pictures of dogs. So yeah, that's the closest dog they had in the training set. Okay, not really impressed? Okay. Generate better images of dogs. What about that? AI is generating better images of dogs. So that's a very, very recent paper. So now you're like really at the cutting edge of deep learning, which is a paper called Big GAN, so large-scale GAN training for high-fidelity natural image synthesis. It's an ICLR submission, so ICLR, which is the International Conference on Learning Representation, which is one of the biggest conference in deep learning, international conference. And this is a paper made by DeepMind, which is a subsidiary of Google. This is pretty good. It's made very popular on Twitter and co. Okay. That's AI, but let's be a bit more serious about what precisely is the definition of AI that we're interested in. And as a French person, before being a computer scientist, I will use some principles of philosophy and namely define the terms you're using. So AI is machine learning, actually. And if you go back in history, Arthur Samuel, which is a very known, well-known pioneer in AI, in 1959 defined, and I think VS gave that definition, it's about computers learning to solve problems without being explicitly programmed, right? And I'm just repeating what VS has been saying, and it's true that the important word is explicitly, okay? And I will, let's say, digest this, rephrase this in my own way, which is actually very close to a professor, it's called Tom Mitchell, which is very, very well known, has defined it in a more formal way. But basically it's software, right? Not magic, it's software that improves with experience by building a predictive model from sample data, okay? And so I basically just like kind of literally translated a formal mathematical definition that Tom Mitchell has been using, okay? So that's more like the overarching definition of machine learning, and what we call AI today is machine learning. Okay, so that's the scariest part of the talk. Do not run away. I swear this is the only equation. I had to put one. This is it. I can explain it in a very high-level terms. It's not that scary. It's basically supervised learning, which what VS has mentioned before. The idea is you have some model, which is a function f, that takes an input x and has some parameters theta here that you want to tune, right? So you want to find the best parameters, theta star. And how do you define the best parameter for your model? Your model, let's say, predicts banana, like VS was saying. And what you want is that on average, which in probabilistic terms you say it's the expectance at E here, expectancy. And so you want the expectation, sorry. And so you want the expectation over your data, D, to be small. So what it means is that if you see all the data in the world and you can measure the error, you want the error to be low. How do I find that model, right? And here, the first thing you do, and that's why you say big data, is because that's infinite data. And you approximate it by having a data set, a small set of data, okay? And then you approximate, well, the error on that data set, right? So this is the sum here. Plus, because you're making an approximation here, you go from infinite data to just a small set of data, you add what's called a regularizer, typically. So something that is a prior, meaning that, well, I know a thing or two about banana, and I don't want to explicitly program my machine learning model, but I can give him, you know, a little bit of help, a little hint to start from, or, you know, some form of constraints on theta. All right, that's it. Math over. This is XKCD version of what is machine learning. So first person asks, this is your machine learning system? Second says, yup, you pour the data into this big pile of linear algebra. I don't know, if I could make the Texan accent, I would do it. Then collect the answers on the other side. What if the answers are wrong? Just stir the pile until they start looking right. Right? So stirring the pile might be getting that sum, right? Sampling or like doing other shenanigans, okay? So in the context of autonomous driving, right? So the lecture series is about AI, but in particular, my talk is about autonomous driving and AI in the context of autonomous driving, okay? So in our context, it's about hardware, software, and data, okay? So let's start with the hardware. Obviously, hardware is cars, okay? And this is, for instance, our Platform 2 prototype from last year. This is our current prototype, Platform 3. And you should see them on the road fairly soon. This is, I mentioned the e-palette, and this is a concept car called Concept I that will demo at the Olympics in 2020. And so obviously the car. And so it's kind of important because people generally like forget that when we talk about autonomous cars, people think about the brains a lot, right? But we're not brains in a jar, right? We are bodies. So our brain is inside the skull and etc. So, and I'll get back to this for robots. It's called the sensory motor loop. And so the car, the body is really, really important. And the compute, of course, is also very important. And so here you see we have a little compute box there. It's like no ugly cables everywhere and whatnot. And here you have like special hardware for running like deep neural networks. And obviously sensors. So sensors, here you see, you know, if you're in Silicon Valley, you've seen many of those cars with the KFC bucket on top, you know, this is the LiDAR spinning sensor. And our Platform 3, you see, has no KFC bucket, but we do have LiDAR, and so these are special exotic LiDARs. I'll talk about that, and I'll explain a little bit what LiDAR is. Actually, we do have a video, so that explains a little bit about the sensors. And I'll let Ryan speak about it.
Platform 3. One was really to radically increase the sensing capability of this vehicle. The jump that we're making in terms of the LiDAR technology that we had in the 2.0 vehicle to what we're going to be deploying on the 3.0 is just a dramatic increase in range and density. We were able to have essentially 4 of these heads at the 200-meter range and the 4x kind of point density. Secondly, to really improve the styling of this vehicle. And then thirdly, to really go to scale in terms of our capacity to really build a fleet of these vehicles. Calty does all the body design actually for the North American vehicles for Toyota. They were.
And I'll stop here. So, so the LiDAR he's talking about, which is inside here, it's called it's a Luminar, so it's a special kind of LiDAR. And the main, you know, theory about LiDAR, the main way it works is it's just laser pulses and you measure the time of flight, and that gives you a point at a certain distance in space, and that enables you to build a spatial understanding of the scene. And it complements really well cameras and radars, but I'll get back to this later. So I just wanted to, you'll hear a lot about sensors, you'll hear a lot about compute, you'll hear a lot about AI, but I think the body itself of the car is really important, which is something that's, a very robotics-y notion. Yes. So in terms of ops, it varies. So of course you tailor the compute because this is at the edge, right? Like VS was saying, you tailor the compute for the actual load you have and for the cooling capacity you have. So the main difficulty in cars is you have enough power somewhat to sustain heavy workloads even with today's hardware, but then you go into cooling capabilities, auto-hardening capabilities, because this thing has to be able to sustain crazy weather conditions, always be on, et cetera, et cetera. So to give you a concrete number, you probably need something between 100 and 300 ops per second, and so, tera ops per second. So, yeah. So but the main difficulty is not so much like how do you get as enough computational power, is this trade-off between computational power and actual power. And so you need to be somewhere below 30 watts for sure, probably below 20 watts. And right now, the only way we know how to do this from a hardware perspective is to reduce the flexibility of the hardware. So is to make some assumptions that constrain the software that can go into that hardware so that we can bake certain things in silicon, reduce the operation set or this kind of stuff. And so that's why you hear about AI chips. In general, it's like you have general purpose compute, right? Like the GPU or CPU, and that can run anything. And then as you go towards the reduced power, like more efficiency, you also reduce, there's no free lunch, you reduce the flexibility. Yes, so in the car today, when you hear about learning, like VS was saying, is like you rarely learn at the edge, or the learning at the edge is very lightweight. So it's mostly about efficient inference workflow, yeah. Yeah, so that's another thing you can do, right, another assumption you can make is that you don't need the full precision, and so people typically can work in half precision floating point, like FP16, or can work in even int8, so 8-bit precision ints, and that's still an area of research. So there are some tools that enable you to do that, but whether they actually work is dependent on the data, dependent on many other factors. So it can work, but it's not a general purpose solution yet. Okay, so as I mentioned, thank you for the questions, good questions. So as I mentioned at the beginning of the talk, I won't go too deep into every topic so that we have time to cover, but if you have some questions, I'm happy to dig a bit deeper. So the hardware, I'm sorry, you probably can't read this, it's too small, but there is basically, in terms of the sensors, there's radar, passive visual, which is the cameras, ultrasonic, and LiDAR. And I don't think it's really important to understand this graph in details, but what this means is that we have many criterions that we care about for autonomous car, like how does it work in the snow, how does it work at night, how does it work in bright daylight, how far can I see, what is the resolution, right? These kind of things. And also what the variables they can capture, right? So for instance, the radar can detect speed, it can give you, with Doppler can give you the velocity estimate. So what matters is that there's no such thing as a silver bullet when it comes to sensors, all right? Even our eyes, which are amazing, it's like 120 decibel of like dynamic range and things like this, which is nuts. We still need sunglasses, for instance, right? And these kind of things. So in terms of sensors, what matters is
there's no silver bullet. You need as many sensors as you can, and they have different specialties, and that's why one thing that's really important is sensor fusion. So one thing you hear a lot about in autonomous driving is sensor fusion. This is the reason why. We need to fuse information from different sensors because they have different strengths. Okay, not diving deeper into this, talk about the software also, high level. Actually, software is such a huge topic because cars are becoming computers. And I will not brush too much about the traditional aspects of software, but obviously super mega important, right? So unit testing, continuous integration, all these things that you know and love are mandatory for good, successful software deployments. We follow them, and it's really important. And again, in this spirit of this lecture series and democratization, the hardest thing to grasp is how deep learning and machine learning has kind of like expanded the capabilities of normal software. Okay? It has not replaced normal software. It is normal software, but it has expanded its scope. So there is this very nice blog post by Andrej Karpathy, who's the director of AI at Tesla, and he has this really cool moniker. It's called Software 2.0, which is like really depicting this kind of like an upgrade on normal software. So machine learning is again, remember, it's not explicitly programming computers. So computers learn without being explicitly programmed. So why is that powerful? It's powerful because when you do software 1.0, let's say you do a planning algorithm, and you say, how do I handle an unprotected left turn? I go to a stop line, then I watch if there's an object, I detect its velocity, and then et cetera, et cetera. So you can imagine this madness of an if-then-else, you know, in the code, right? That, by the way, is called expert systems and failed really badly. IBM almost died because of their bet on this and their failed bet on this. And so that doesn't generalize, right? That doesn't work. Because then there's a question about, what if it's an ambulance? What if the person inside the car is waving at me to go? So all these edge cases are something that machine learning, if it sees it in the data, even if you don't tell it, oh, in the case it's a police officer that's waving at you, yeah, sure, you should do that, right? That's common sense. Or maybe that might be even in the DMV regulation explicitly. So if it's in the data, you have not programmed it explicitly, but it can actually learn how to react to this. And furthermore, it can learn to react so that it optimizes a given objective, let's say the safety, travel time, and all these kind of things. And so you start from something that might be worse, but with accumulated data, accumulated experience, because again, it's learning from experience, the software becomes better and better. Handles more edge cases, et cetera, et cetera. So that's the important mindset. And to convince you, I said I had only one equation, but that was not the end of it. I also have code. And I'm going to make you sweat. A little bit. Nah, this is actually just, again, like in the spirit of democratization and demystifying, I will make you code maybe your first deep neural network. Who has already coded deep nets? Wow. Experts. So, okay, this is PyTorch. PyTorch is a deep learning framework that has been developed by Facebook. And it's our actually framework of choice at TRI. And here, what you'll see is what this software 2.0 means. So we will define software 1.0. This is software 1.0. This is Python, right? This is normal Python language. But as a result of this, as a result of defining this and learning this, you get an artifact, which is weights of the neural network. Remember that theta in that equation, right? Well, that's writing this code is going to generate you that theta, and then that software 1.0 coupled with the generated weights of the neural net is software 2.0, right? And so here we go. Ready? So first block, import. So for those of you that can see, right? So import torch.nn as nn. So nn is neural networks. So you get the neural network part of the torch library. And you just like use an alias because like torch.nn is like a mouthful, so you just say nn. So here this block is basically just reusing some libraries, right? Standing on the shoulder of giants. You don't recode everything from scratch, don't reinvent the wheel and these kind of things. DRY principle, right? Don't repeat yourself. So I told you it was software 1.0. Okay, second part, class net that inherits from nn.module. Then you have a constructor, and then you define some attributes, self.something something, right? So here you're defining layers, right? Functions with parameters to tunes. So again, deep neural nets are basically a sequence of operations that we call layers, right, that are stacked one after the other. The output of layer 0 goes into layer 1, and that goes to layer 2. All right. Next, you have another method. So that was a constructor, just setting up the scaffolding. And then you have a forward method that will tell you how does my image flow through the network to compute my prediction. And so you define basically just a set of computations. All right, when X, my image X, it goes through a convolutional layer, conv1, that I defined here. Then it goes through a max pooling operation, and then it goes through a ReLU nonlinearity. These are all just mathematical operations, right? So I'm not going to go into the detail of them, but this is just like, hey, take that image, transform it into something else, like a transformed version of an image, like a filtered image, and then apply some other transformations that make it more meaningful, and again, okay? So this is, by the way, called inference, right? So that forward pass is the inference that VS was talking about. And yeah, you just defined a neural net. Congrats. I think you deserve a round of applause. You are true hackers. Okay, so what is that bottom part here? This function, def learn an AI. It's a function called learn an AI that takes as input a data loader. So it builds your network, that's your model, right? And you get an optimizer, because remember, software 2.0, you don't get just a starting point, you optimize from data. So you iterate on your data loader, you say, feed me data, feed me data. Data comes in the form of raw data, like let's say the images, and target, let's say banana in the previous case we've seen. And then you do a little bit of magic, but that's like boilerplate from PyTorch, where you just say, hey, give me your prediction, right? So the output, which is just feeding the data through your model. And then remember that big scary expectation and the loss, etc., like the big equation? Well, here it is. You just say, hey, measure your error between your target and your prediction. And based on that, please nudge the weights, adapt the model to do better next time, right? Make less mistakes. And the way that this is done mathematically behind the scenes, but you don't have to do it, it's done for you automatically, it's called backpropagation, okay? And automatic differentiation uses backpropagation to just nudge the weights just the right way to minimize the loss. All right, that was the second hardest part of the presentation. The rest should be smooth sailing from now on. So, great. What can you do with that, right? You can do panoptic segmentation, for instance. So what is panoptic segmentation? So this is, again, like all the examples that I'm giving are really, really cutting edge. It's like few weeks, few months old, okay? Because that field moves fast. If you are watching the recording of that presentation in 1 year from now, you'll be like, so old, so 2018. Yeah, that field moves really fast. So panoptic segmentation is a problem that we really care about in autonomous driving, which is we want to understand the scene. We want to say, what are these pixels? Are these road pixels? Are these sky pixels? And we don't just want to understand the stuff, you know, like we want to understand the things. Is this a person? Is this a car? And these kind of things. And panoptic segmentation is this task of taking an image, get me an understanding of that image in terms of, you know, you go from these RGB values, right? Red, green, blue, that says like this is red of the car paint, but this is like red of the traffic light. What's the difference between that red and that red, right? In terms of the pixel value, it's the same. So to understand these semantics, you learn a neural network that maps from this image, remember X, to the target, which is this, which is a semantic mapping that says, oh, that pixel is a road pixel, right? And of course, it's all probabilistic because we can make mistakes, and the learning is statistical in nature. So here, this is just the best predictions. But behind the scenes, the neural network builds a distribution over all the possible interpretations of the scene, and we just act on the most likely ones, if they are likely enough. Another super cool thing you can do is, and that's again a submission, a very recent submission in my team that we did for the leading conference in robotics called ICRA. And here the idea is you want to take an image here and you want to predict how far are each object in the scene, right? So you want to say predict per pixel the depth of the object. Like if you were casting a ray, if you had a LiDAR, how far would that LiDAR tell me this point is? Now, if we have LiDAR, why do we do this? Well, again, because every sensor lies, and LiDAR is sparse, and cameras are complementary. So if you could do it from a camera, that's great. You can do sensor fusion. So here you see basically that we learned a neural network to take just that single image and output the depth of the scene, right? And so if you have the depth, you know the obstacles, you know many, many things. By the way, if you know the depth, you know where the pixels, they correspond to points in 3D. So you can build a 3D map. And the beauty of this is this expression here, self-supervised. How do you provide examples of banana? You just get pictures on Google and you feed banana. How the hell do you get supervision for depth? Like, do you go and you ask on Amazon Mechanical Turk, you're out crowdsourcing workers. All right, for every pixel in that image, you got to tell me precisely in meters, not in inches, not meters, right? How far is that pixel in the scene? Go. This is impossible, right? Like, this is actually physically, geometrically impossible. So the way we do it is we do it by saying, well, it's impossible, but geometry exists, right? Like, through the rules of 3D geometry apply to you whether you are anywhere in the world or whether you're a neural network. It's always there. It's always true. So what you learn is you learn a model that predicts something, and you say that something needs to obey the law of geometry. And that might not be enough, but actually in that case, that's enough. If you just say my prediction needs to be a law of geometry, then you can get actually depth. You recover depth. And that's essentially for free because what you're using as supervision is not a label that's provided by a human. Instead, for the supervision, you use fundamental laws of light. As simple as that. And so supervision does not necessarily mean manual, tedious labeling. And in some cases, it is actually impossible. Supervision just means a distilled source of additional information that you have, because at training time, you're privileged. You have this privileged access to information that you might not have at inference time, because, for instance, you cannot reason on a lot of data set and recover some rules of geometry. But at training time, if you have some source of information that adds extra information than just the pixel values, then you can do like things that are in between unsupervised learning, where I just give the pixels and you're on your own, or supervised learning, which is I provide you the ground truth, the actual labels that you need to regress. And you just don't understand the problem, just say, aye, sir, okay? Yep. Yes, so all you see here is from a single camera, right? No, so if the LiDAR was telling you where things are in 3D, and you use that for training time, that would be supervised. But in that case, and you assume calibration, you assume you even have a LiDAR in the first place. In that case, we don't use LiDAR at all. No LiDAR was harmed to do these videos. Yes. Yes. So no, so but that's okay. In that particular instance, no, but there's a lot of work that indeed do that. So any assumption you can make about the scene, right, which we would call a prior in Bayesian terms, in like probabilistic terms, it's like something that you know to be likely true if you were blind, right? Like I don't show you data, what could you guess? I don't know this, right? So if you have that information that's useful in the system. But it's also constraining in terms of the deployment, right? If you say that I need to have that camera always at the same height, because I need to know the height so that I can, and the ground plane information. So it doesn't work in Lombard Street, and it doesn't work with a smartphone, because if I mount it differently in behind my windshield, it's not gonna work. So all assumptions are also constraints. So they're powerful information you can inject in the system, but they're also constraints that limit the applicability of the method. In that case, we use two things. So we use, okay, I'm going to get lost into the weeds. I think I can take this offline because it's super, super, super interesting. And if I start there, yeah. All right. But excellent question. Thank you. All right. So that being said, I talked about machine learning, right? Where does it fit in the autonomous driving picture, right? There is this notion they call this the spectrum of ML entanglement. It's everywhere. It can go everywhere. It doesn't mean it should, but in theory, it can be. It's very general in its applicability. Okay, and so in TRI, I have defined basically it's kind of like guiding principle that I call Newton plus Hinton. So for those of you that don't know, I mean, okay, Isaac Newton, I mean, okay, you know. And Geoff Hinton, he's considered as one of the godfathers of modern deep learning. He's been working on neural nets for like decades and decades. And so here the idea is Newton plus Hinton is like there's a spectrum over which ML can intervene, and that spectrum actually is determined a little bit by the system level consideration. So the Newton side over there is what you call engineer what you know, right? Again, the ROI, and don't reinvent the wheel. You know things about the world, well, duh, you know, like if you don't need to rediscover gravity every time you're taking a step. So these kind of things is like if you know it, you can engineer it, code it, and like hard code it into the system. You don't need data for that, great. Now on the other end of the spectrum, there is learn what you don't know, right? So engineer what you know, learn what you don't. And so on that spectrum, there's supervised learning, obviously. If you say, oh, for driving, I know that I need to have a traffic light detector. Oh, that traffic light detector is like traffic lights are going to be typically around there in the image. Oh, traffic lights can be either red or green or yellow. And they can only transition from red to green and green to yellow and yellow to red. So these are all assumptions, and you could code them, right? And that would be in the supervised learning regime, and you would say, okay, traffic lights, and for traffic light, just, I give you a lot of examples, and you know the closed world interpretation of what a traffic light is. The end-to-end learning is on the opposite spectrum, is actually, well, what if I don't tell you what a traffic light is? I said, why? That sounds stupid. I know what a traffic light is. Well, have you seen all the traffic lights in the world, and have you seen maybe the ones in Japan that are kind of crazy, and there's like really weird traffic lights everywhere, and it's, oh, so you mean I have to travel across the world to know what a traffic light looks like? So you have many edge cases, and so you might want to actually have this other spectrum, which is like, if you don't really know what a traffic light is, you shouldn't hard code it. So, and on the end-to-end learning side, actually in driving, there's a long history of using that approach to just driving. What does driving means? I don't know, it's just taking the steering wheel, turning the steering wheel, the axle, staying on the road, don't hit stuff, don't get hit, these kind of things. Well, it could be just, hey, you know how I define driving? Look around you. You have many people that drive, just drive like that, right? And so that's also called behavior cloning or end-to-end driving. And actually there is a really cool work done by Dean Parmelau at CMU that you might have heard about, like NavLab, Alvin, all these kind of things. They actually did like cross-country with this. It's a single neural network that just learns from an image to map steering and axle. And how did they learn that? Well, by imitating how humans steer and accelerate and brake. On the other side, obviously, there's just something interesting, which is the other end of the spectrum, because that's a totally valid spectrum. Positioning yourself anywhere along that spectrum is a totally valid approach with different trade-offs. There is, oh, you're running out of battery. I hope you are not running out of battery. Ernst Dickmanns, German engineer, had a huge European project with Mercedes-Benz, and he basically in the 90s was doing what Waymo, Tesla is doing today, right? So there's nothing new here. It's like a computer vision system that is actually learning to drive on highways and is able to drive on highways. And they did, like I just saw, like NVIDIA did an 80 kilometers loop, etc. They did like highways in Paris. They do many crazy things back in the 90s, all right? with trucks, with Mercedes-Benz, like loaded with like, I don't know, something that's like a 10th as powerful as this thing. And yeah, that's amazing. And so this is totally valid spectrum. There's interesting questions, which is, well, if you're iterating on these two since like 30 years, why don't we already have self-driving cars? That's an interesting question. And maybe we'll get back to it and debate it a little bit later. And in the middle, actually, so that like big thing here would have been a big hole if I didn't put something there. I think it's kind of like the reason why today there's also a revolution is because of representation learning. So deep learning is often said that it's the most useful for representation learning, which is learning how to abstract the world, right? So here it's like a very strong abstraction that you decide what the world is, and you're making a closed world assumption. A traffic light is this. Hey, what about this one? I don't know what that is. That is not a traffic light. Oh, it is a traffic light. No, it's not a traffic light. Versus here, which is just, I don't care, man. I don't know what traffic light is. Just turn there. Why? Just turn there. That's fine, right? So in the middle, you have this, what is actually a good representation, right, for driving? And you can learn some of it, but you can also engineer some of it. And that's a very big spectrum, and why actually I think the most interesting research is happening in that space right now. Okay, great. So let's take a little step back. Here, one thing that we're doing is, I talked about research a little bit just now. We're doing, I don't know if you're familiar with Pastor's quadrant, but it's basically, you have different ways to combine research and development. And Pastor's quadrant is really where autonomous driving is at. It uses inspired basic research, right? It's like, we know what we want to do. We want to do autonomous car. So the use is inspired is there, right? And basic research, because we still don't know how to make a fully autonomous car everywhere, every time, etc. We're making progress in some restricted domains, but we still haven't cracked that nut. And so how do we combine this research that's in representation learning in AI that I just talked about with, what we actually want to do, like cars, robots, or like in our case also work on material science, so batteries, with this thing, with AI, deep learning, PyTorch, whatever data. And so yeah, data, right? Duh. It's like that's how you bridge the gap, right? Because here what's missing in that equation is obviously data. So remember the definition, okay? AI, machine learning, software, not magic, that improves user experience by building a predictive model from simple data, okay? So I'm talking a little bit about data now. Data is ML's alpha and omega, okay? That's a very loaded slide. I'm not gonna go into details, but basically, again, that spectrum that I mentioned before, it's the same in ML. You can have things that you code by hand, like model structure or learning algorithms, so the algorithm to learn. And, you can have data-driven approaches to actually learn the model structure itself. And you've talked about, there was an example of AutoML service in cloud. Well, that's Google Cloud, that's what they do. You can even learn the learning algorithm. So it's meta-learning, it's like learning to learn. And obviously you need data. So important thing, is it magic? I've been using the term, it's not magic, it's not magic, it's not magic. At this stage, you might be wondering, oh, it's 9 p.m. almost, it's magic. Okay, it's not. And how can I convince you it's not magic? There can be a simple question, right? Magic is creation ex nihilo, right? And Lavoisier, rien ne se perd, rien ne se crée, tout se transforme, right? Which is, I don't know the English translation, but I'm going to make it up on the spot. Nothing creates itself, nothing destroys itself, everything transforms itself, all right? He's the forefather of modern chemistry. And so here there's this question, right, which is, can the representation be better than storing the data, right? Can there be ex nihilo emergence, singularity, killer robots, Terminator, wow, okay? So can something magical emerge beyond what you have seen in the data? And the answer is no. SpongeBob says so, no, okay? I feel you're not completely satisfied with that answer. You're a good scientist. So the medium answer, which is a bit more scary than SpongeBob, is the data processing inequality. All right. So from an information theory perspective, Post-processing cannot increase information. We know it, right? It's often actually understood in the Silicon Valley and in developers, as garbage in, garbage out, right? That's classic. Well, that's it. You could say, oh yeah, you mean the data processing inequality, right? The cross entropy, Yeah, okay. There are longer answers if you really want to sound fancy about, again, this information theory perspective. So information bottleneck, separation principle, et cetera, et cetera. These are theories at this stage. These are theories that are from my perspective, the leading potential explanations for why deep learning works so well. It works really well. We're trying to understand completely why. We're not there yet. But these are some of the leading theories. But long story short, because it's not magic, it cannot hallucinate new things, you need scalable data, scalable supervision, or high sample efficiency solutions. So a little point again on autonomous driving, like taking steps from general AI, autonomous driving. So now we're getting back to autonomous driving. You could say because you cannot be better than data, that's hopeless. You can't see all the data, but you cannot see all the data, but you can see a lot of data. And actually, when you think about it, Toyota being the #1 car manufacturer in the world, right? So we have 100 million cars on the road today. We sell 10 million cars every year. If you do this very, very, very conservative back-of-the-envelope estimates, like cars are 95% of the time parked and all these kind of things, and you have a single camera in the car that uploads minimal amount of data, very subsampled because of the network capacity and everything, you get to numbers that are actually way north of 22 petabytes per day. And that's not just to scare you with numbers that, you think like, bullshit, So you can do it at home, you'll see, it's interesting. And that's 10x YouTube per day, right? So every day YouTube gets like 400 hours of video per minute uploaded, right? In HD quality, if you look at their codec statistics, etc., that's like 2.5 petabytes per day. Obviously here you have this major problem, and the cars now today have sensors, right? So like they have this, so it's not like imaginary sometime in the future, it's like today. Right, and so this big question of label all the things. Should we label all the data? Should we have humans explain to us what all the data is, so that the system can learn? And that's why I mentioned self-supervised before. It's obviously a way out of that dilemma. Data is precious, okay, and again we need this amount of data. We need a lot of data, and the reason is so this is the RAND report from 2016, and basically you cannot. So humans, I mentioned, like humans are pretty terrible drivers on one hand, but they're also pretty good drivers on the other hand. Not everybody's drunk and tired all the time, right? So, or texting, whatever. So it turns out that our accident rate is fairly low, and we use the car a lot. That's why there's a lot of deaths. But the percentage, the relative percentage is very, very low. And so therefore, this creates a problem for a statistical method, like a learning-based method for autonomous driving, which is we cannot guarantee the car is safe. We will not ever be able to guarantee the car will always behave according to specification, because the world is statistical in nature and the algorithm we are developing is statistical in nature. So the only way we can get some confidence that we're actually improving things, we're saving lives, and we're not making it worse, and we're giving a safe solution, is testing, testing, testing. That's the only way. And the problem with these statistics is that we need to test like hundreds of billions of miles to be able to say with statistical certainty, yes, you are, let's say, 10 times safer than a human, right? And it's great that people now are starting to be able to test on, maybe like the largest one, maybe Waymo tests on 8 million miles or something like this. It's awesome, it's great. It's 0.00001% before we can claim, scientifically speaking, that it's safer than a human, okay? So that's really, like, again, for you as it's not just about democratization, it's also about having your, I'm a big fan of Jon Stewart, when it smells like bullshit, now you know, okay? So really use your critical sense and don't be fooled. The numbers are always there and numbers don't lie. So that's why our CEO, Gil Pratt, which is a former head of DARPA, and he has this expression called the trillion-mile challenge, right? It's like, you need 1 trillion miles. But imagine this, it's like you make a new car, You need 1 trillion miles to test it. Oh, you change one line in the code. You need 1 trillion miles. So this is nuts, right? This is madness. This is never going to happen. If you really want this to be able to say with statistical, some notion of statistical confidence, it's just like, why are we even bothering, you know? And so there is a solution though, right? There is a possibility, which is, again, testing, software. It's software, right? So it doesn't mean necessarily I have to risk people's life whenever I deploy, you know? You can have data from ordinary drivers that tell you a lot of statistics. You can build data sets and you can see how well would I have fared in that situation, hypothetically speaking, let's say for your object detectors or whatever. We have test cars with professional drivers. Everybody has test cars. We can test in closed course. We can test on the public roads, within the realm of what is legally allowed. These are just millions of miles, right? This is, again, like compared to the 1 trillion mile, that's nothing. So obviously you need simulation. It's not like a view of the mind. It's not like, oh yeah, I think it's a bit, no. Like if you ever want to be able to say with some degree of statistical confidence that your system is safe, you need simulation. It is a must. It is a requirement. And so obviously we're talking billions of miles, etc. And all the players are kind of like doing it. I mean, all the serious players are doing it. And so you need it in the cloud and obviously to do it at scale and every night. And you can imagine this is a crazy continuous integration process and deployment process, right? So simulation, I can do some description about like some past work I did. So you have some video and you say, all right, it would be great if I could change the position of that car. What if it was raining? So you can do like things that the economists call ceteris paribus analysis, which means what if analysis. So intervention calculus. It's like, what if it was a girl here? What if it was a basketball here? So obviously you can't do that in the real world. You can't modify the past. But if you can recreate the matrix, if you can recreate in simulation something you've seen, and it's actually a full virtual world. It is not just I made an image that looked like the image I've seen. If it is actually, like imagine you create a game, right? Inside a game engine that's called Unity here, then you're in full control. You're in God mode. And you can say, oh, I want to know exactly what all the pixels are, what they mean, how far they are. And you know it, why? Because you created that world, so you're in full control. And then you can start to change conditions. You can start to say, hey, what if my camera was miscalibrated and had rotated, right? What happens? How many more people would I have virtually killed, right? And you don't need to actually kill people. You just need to know that, that would have been bad. What happens in the morning? What happens at sunset, right? Does my dynamic range of the camera, is it handling this well or not? With the overcast weather, oh, there's no more shadows. Actually, my system kind of like needed shadows. Oh, what about fog? All these kind of things. And you can really do the same situation you've seen in the real world over and over again, and changing one thing at a time. Obviously, you've seen the difference between the real world and the virtual world. Well, that's called the domain gap, and you have to have a model that can address that domain gap and works as well in simulation and the real world. And so you remember this dog generating GANs, generative adversarial dimension? Well, you can use it to adapt a simulated image towards a real image and then have models that work in the same way in the real world and the virtual world. I'll skip on that. Obviously, all this kind of thing is massive, right? Running all these simulations, running all these trainings, etc. So we at TRI, we are using an AWS-based stack. That's a must, I think, at this stage for us early on. We can't really develop like these crazy data centers, etc. And this enables us to really bootstrap really quickly and really do our research at a very large scale. All right, one tiny tidbit on data before I wrap it up on data. There is, I mentioned that deep learning, we don't completely understand why it works. It does work. Again, it's an experimental fact. Why, right? We have some theories, we have some ideas and everything, but some people say it's alchemy, right? And if you look at it from a historical perspective, you remember I said Newton plus Hinton. Who's the alchemist? Newton was an alchemist. And so actually, if you look at Newton for his F equals ma, right, his Principia, etc., like how did he derive the universal laws of gravity? He actually derived from Tycho Brahe, which basically just looked at the stars with his eyes and just like painstakingly wrote like all the positions, etc., etc. They built a huge data set by hand. That data set, Kepler saw a pattern and says, it seems like a good model might be this convolutional neural net. No, he said, like, this equation. I think it explains the data. It's a good fit. It minimizes the error of the trajectories. It builds good prediction. And then Newton said, oh yeah, it actually builds good prediction. And you know what? There's actually a fundamental reason for it. It's because that's how the universe works. Boom, all right? Data, alchemy, model. So we're probably in the age of alchemy right now in terms of AI, and we haven't yet ushered into the era of, chemistry, where we understand why we can change that metal into something and not like lead into gold, right? So okay, that was a very long section on how. The other sections are a bit shorter. It's going to go much faster, but this is the most important one because this is about really like the technical side of things, right? How are we going to get there towards autonomous driving? So AI, obviously, right? But I hope I gave you a little bit more of a glimpse on what exactly AI means and what are the special parts. So the hardware, sensors, compute, cars, infrastructure. I haven't talked about infrastructure because I didn't have the time, but you've heard about V2X, V2, vehicle to infrastructure, et cetera, et cetera. So you can have the infrastructure helps you. We as human need it. We, for instance, have traffic lights and traffic signs. Otherwise, that would be mayhem. So autonomous cars eventually, for sure, will have that too. Software, deep learning, cloud, OTA. I haven't talked about over-the-air update or security or all these kind of challenges. Data, I talked about fleets, consumers, and simulation. How much time do I have? Oh, okay. All right, let's take another quick break then. A few seconds. You can stretch, you can stand up, rotate your neck a little bit if you want, and in the meantime, you can read this. These are some funny XKCD self-driving car milestones. I won't read them all, but we can take a quick break and you can have a look. I can tell you my favorite one. There is, automatic emergency braking, highway lane keeping, self-parking, full highway autonomy, first sex in a self-driving car, full trips with no input from driver, full trips by empty car, self-refueling empty cars, an empty car wandering the highways for months or years until someone notices the credit card fuel charges. Is like forgetting to shut down your cloud instance. It's the same thing. You get this bad surprise. Cars that read each other cars' bumper stickers before deciding whether to cut them off. Better think twice putting that Hillary sticker. Autonomous engine revving at red lights. That would be fun. Self-loathing cars. That's really when you hit AGI. It's like at this stage, it's like, why am I stuck in traffic? But except there's no one in the car. Autonomous canyon jumping, and cars capable of arguing about the trolley problem on Facebook. I will not talk about the trolley problem. It starts with troll for a reason. All right. Okay, so we talked about the why. We talked about the how. Now we can talk about the what. Okay? Sounds a bit weird. Normally you start with what. Okay, what are we talking about? Then how? How are we going to build that thing? And then why? Oh, yeah, and by the way, that's the reason. I prefer to start like, why are we here in the first place? How are we going to get there? And, okay, can you tell me what we're talking about now again? So, very simple. There's one thing you want to remember about autonomous cars. It's this slide. It is a robot. It's a transportation robot. Simple as that. That's it. That's really all there is to it, okay? And what is a robot? Is it like, hey, great, you define something with something else that is not better defined? My washing machine is a robot. It's not a self-driving car. So a robot is a sensory motor loop. So I hinted at this a little bit earlier. So, like early on when AI really started, like Turing, et cetera, people thought, hey, intelligence is about these abstract concepts, et cetera, the body is dirty, all these kind of things, right? And interestingly enough, that's kind of like more Western culture and philosophy. Eastern culture and philosophy actually have a, in my understanding, limited, have a much like nicer view on the importance of the body, and there's this notion of embodied cognition. You know, Descartes, French philosopher, was talking about like the separation of the mind and the body, but actually it turns out that modern neuroscience has proven the French wrong and proven the Eastern philosophy correct, that we are embodied creatures. The body and the mind, the body is part of our intelligence. And so sensory motor loop means that it is the way we act and the way we perceive and the way we think are all connected. And it's impossible to actually separate them. So perception, so I'm going to go a little bit more into details compared to what VS was talking about. Perception, making sense of what's around you. Prediction, reducing uncertainty about the future. Planning, deciding, all right, how do I do what I want to do? Decision, all right, I'm going to commit to doing that. And then action, which is actually executing. And this is not a feed-forward stream. There are feedback loops everywhere, right? There's like a lot of research, especially in neuroscience. So this is a well-known kind of notion now accepted in AI, not like in modern AI, not in old symbolic AI. There's this kitten carousel experiment, which is kind of funny, which is a neuroscience experiment, which I encourage you to look at. You just search kitten carousel experiment. But all these things are basically just like saying that we are sensory motor loops. A little bit more details about self-driving cars this time. What is perception? So perception is making sense of the present. I've shown you the panoptic segmentation stuff before. This is it. You see, again, like here, you see the traffic lights, the traffic signs, the poles, and many other things. You can integrate, again, like this is a view of our cars, sensor fusion. We merge the panoptic segmentation, LiDAR, many, many different things, just so that we understand what the hell is going on here, right? And then you have prediction, right? So a professor at MIT we're actually collaborating with is called Josh Tenenbaum, and he has this really nice expression that talks about the game engine in our heads. We are extremely good at guessing what other people are going to do. It's called the theory of mind, that we think that someone is going to cut me off because if I was an asshole, but I'm not, I would totally cut myself off, right? And then you're going to be like, oh, I'm not going to let that happen. And then you press on the gas, right? So when we do that, whether we're completely conscious about it or not, and I'll get back to this, we're running simulations in our head. And those simulations are actually just from my perception, from my current understanding of the present, I'm going to predict the future. Of course, you cannot predict the future. So that's what I wrote here. You reduce your uncertainty about the future, right? And so in self-driving cars, there's future trajectories is something that we really care about. And there's many different works on that in the computer vision and machine learning community. We did some fun experiments ourselves. That's the basement of TRI, where we did some like trajectory forecasting and end-to-end kind of things, experiments. This is more like a saliency to predict what are parts of the scene, how they the importance on looking at these parts of the scenes change over time. Might not be super interpretable, but yeah. All right, and I put Saruman here for those of you that are Tolkien fans. So the California, that's a really good question. How far, oh yeah, I forgot to repeat the questions. How far in the future should we predict? It depends. If you want to trade Bitcoin, not far. If for driving, California Handbook of Drivers says 5 to 10 seconds in the future. And so that is a very deep question, actually, because in driving, you have this benefit of having a structured environment. The roads, right? It's not like we're just not moving in water or space. And so in that case, there's a weird equation, which is time equals space. In the sense of that's why do we need such a high resolution image in the first place, is because a car far in the distance, we want to have more pixels so that we can really detect it. And why do we want to see that car far away in the future, far away in distance? It's because if I see it coming from afar, I can build a history of its motion and then predict the trajectory more reliably. And I don't need to know when that car is going to be at a given position. I just need to know, for instance, a time to collision is very, very far in the future. So it's depending on how you formulate the problem, It can be very easy to do way more than this, or it can become actually really, really hard for things that are really close to you. So imagine like a bicyclist, or imagine something stupid. Like right now, you can predict the future, blah, blah, blah. You cannot predict what I just did, right? The only way to predict it is if you knew me really well, you had seen a previous talk, you had seen that I'd already used that example, and said, oh, okay, he's going to do that trick to show that you can predict the future, right? So AGI, right? And stalker AGI, you know, like weird. 5 seconds in the future, that's a general guideline given to human drivers, but for autonomous cars, depending on the perception task, or the, let's say, the agent or the variable you want to predict, it can be more or less, or formulated in a different way than just predicting the future. Like predicting the distance, for instance, could be an equivalent in that case. But very good question. I just brushed up on it. It's really, really big and deep question. Prediction is the most open problem right now in autonomous driving, by far. Okay, and then, okay, great, you have your prediction, you think you have like, I think I know these people are going to move this way, I want to go there, so how do I even start to decide, like, how do I get there, right? What should be the trajectory I should take, right? And again, you have the spectrum, right? You could do like program exactly, oh, if you are in this situation, go there and then go there and like go through free space, et cetera, et cetera. Or you can also learn it. Very recent paper by Berkeley, again, like extremely recent, a few weeks old, where it's about like learning to plan like a human would plan by learning from demonstrations. It's called imitation learning. And of course, you know, what was it? It was Eisenhower, right, who was saying a plan is useless, but planning is essential. I think something like this. And so I would say a good plan is great, but if you don't have control, if you cannot execute on it, it's worthless. I think Sam Altman was also saying this recently about startups. You know, like you have vision, great. If you just have vision, you make a blog post. Then you have like planning, which is great, but then you need execution. So you need all these things. And about self-driving car, when you have vision, you have the perception and the prediction, you do the planning, great. Then you need to exercise the control to actually execute on the decide plan. And this is a really hard problem. There's a lot of math, there's a lot of like really good approaches that are solid, but again, in the real world, in the unconstrained wild world, it's really, really hard. This is a super cool project at Stanford that also we're collaborating with. And this is a DeLorean, yes. And this is autonomously drifting a DeLorean. This is really, really hard to do. Very, very hard. Like here, Newton would be crying because the equations for this are madness, like slippage, etc. Like friction is a beast. So here you have control algorithms that push the limits in terms of physics, but also like machine learning also has a place there, right? Because this is like a special surface, that they know everything about it, etc., etc. So what imagine like black eyes and all this kind of madness that we deal with. Okay. Maps, I should mention this, right? Obviously, super important part of the equation. And in particular, when it comes to AI and machine learning, there's a really important problem that's called SLAM. Which is an acronym for simultaneous localization and mapping, where you want to have the car that, you know, maybe has a prior in terms of the map, but then he needs to know where it is and register its own local map to where, you know, it is in the real world in terms of like a preconceived map. And so that's a really hard problem. There's many startups in that space, in the space of mapping, HD mapping. But in any case, it's also a core competency that's really important. Even if you can buy maps, you still need this SLAM capability in the car. Oops, without the music. So I mentioned a little bit like certain things might be harder than you think, right? And perception, et cetera, et cetera. So there's this thing called Moravec's paradox, which is from Moravec in 1988. There's this surprising fact in AI that I mentioned before, symbolic AI, people that were like thinking, oh, damn, we made a checkers algorithm. Today, checkers, tomorrow, the world, you know? And actually, what decades of research in AI have taught us is checkers, chess, even Go. You've all heard, I think, about AlphaGo. It's easy. Not for you, not for me, or especially not for me. After AlphaGo, I said, oh yeah, Go sounds so cool. Let's buy a Go board. Yeah, used it twice. Then there was, you know, very hard for humans. Not hard for machines, because this is symbolic, right? And this is actually fully observable in these cases, right? And we know the rules, right? Perception and mobility, on the other hand, having a robot that walks, right, on 2 legs, really, 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 really hard, right? This is a surprising fact. It's super easy for us. So, and you've seen, okay, this is the DARPA Robotics Challenge. You've seen like robots falling over, etc. So, the question here is, really? Like walking is hard? Like seeing it's a banana is hard? Go playing is easy? That doesn't make any sense. But again, it's a fact from experience, from scientific experimental fact that we found over decades of AI. So why, right? What would be the explanation? Big data, right? Like, oh, what? No, come on, that guy's a hoax. His credibility score is going down as he speaks, you know. We should have, by the way, a credulity score for audience too, right? Okay. So the reason I say it's big data, right, is visual perception. Basically, we, as you know, through the evolutionary process, we have been through 540 million years of data for training our visual perception system. And bipedal movement, right, like starting to walk on 2 feet, etc., like 230 million years of data, okay, and evolution. Abstract thought, 100,000 years, right, like way, 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 way less. So that's the main kind of reason why we believe this Moravec's paradox is existing, because, again, we go back to this notion of embodied cognition. This body, I know it doesn't look like it, but it's a super sophisticated machine that resulted out of, you know, millions of years of evolution. And in that case, the visual perception has a lot more training data than the abstract thought. Okay. And there's this interesting also book that you might have heard about, Thinking Fast and Slow, from Daniel Kahneman, which is a 2002 Nobel Prize winner for inventing behavioral economics and destroying the theory of the rational economic agent. And that basically also talks about how, and again, this is a true scientific fact, we spend 90% of our time in system 1, in autonomous mode, automatically reacting to things, right? And that's energy efficient, that's fast, and we're optimized for it. And then 10% of the time, really thinking hard and consuming that glycogen that is precious. Yeah, so that's a great book. And it goes into basically the same line as Moravec's paradox. There's this, again, there's an XKCD for everything. So there's an XKCD for this one, which says, when a user takes a photo, so I guess that's the manager and that's an employee, or that's a VP and that's, I don't know, like Rockstar product manager or something. When a user takes a photo, the app should check whether they're in a national park. So sure, easy, just look up, give me a few hours. And check whether the photo is of a bird. I'll need a research team in 5 years. And in CS, it can be hard to explain the difference between the easy and the virtually impossible. That's Moravec's paradox. All right, so I mentioned robots, I mentioned how it's things that you think are easy are hard, and vice versa. Now, they're not just any kind of robots, right? Obviously, cars are transportation robots, as I mentioned. So what do they transport? They transport stuff. So they can transport, like this, you have the trucks, right? So Otto, Waymo, this super cool truck from a Swedish company called Einride. It can transport goods, last mile delivery, autonomous cars, you've heard about this. This company called Neuro. And then, you know, it can do a mix of people, stuff, etc. Reconfigurable. It's not necessarily, it has to be custom tailored for a single thing. Transport people, so you have personally owned vehicles, obviously, that are going to be more and more autonomous. You have like ride sharing, so Waymo, Uber. You have also shuttles. So actually, there are autonomous cars in the world deployed in production right now. They exist. For instance, May Mobility is a company that was spun off at TRI and that we're funding now. And this company is basically has shuttles in operation that transport people. And it's fully autonomous. There's another one in University of Michigan by a French company called Navia. If you go to Ann Arbor in Michigan and you go to the campus, you will see them. They're real. They go around and they transport people. And that's low speed, right? So that's the reason why they can be deployed with current technology today, is because they have limited operational domains and very low speeds, okay? And that's why they can predict the future, in a sense, because their world moves slower. I got to talk about the automation levels. Level 1, level 4, level blah, blah, blah. You've seen about this, right? The SAE levels. I don't fully understand them. I guess my credibility score is again going down. And I have a better one, which is level 0, you drive, right? This is the dumb car, right? Level 1, feet off, right? Cruise control, adaptive cruise control, right? Most of you that have cars that are fairly recent, you have that. Level 2, hands off. So you take the hands off, you take the feet off, right? So it's lane keep assist plus cruise control equals autopilot. That's Tesla, okay? Level 3, eyes off, right? So although technically Tesla, you have to keep the hands on and blah, blah, blah. Okay, level 3, eyes off. Like, I don't need to pay attention, but I need to be behind the wheel in case the car tells me, hey, John, I think you might want to take over now. You have 3, 2, 1. So that's level 3. A little bit dangerous. A little bit dangerous, especially if it works really well. Then you're like, and then, what? Sorry. Yeah. And we all know how it goes. It actually has already killed people. It has already happened with like Uber fatality, etc., with the safety drivers not paying attention. Okay. So that's level 3. So you hear a lot of the prototype cars that are being developed, etc. They're level 4, level 5. They're actually level 3 de facto because they have a safety driver that needs to intervene at any moment. Level 4, brain off, right? It's like literally you can take a nap. That's fine. The car will be basically just waking you up gently saying, John, yeah, what? I don't know where we are anymore. I safely parked on the side and you might want to take over. Level 4, right? Brain off. So you need to have the fail safe, etc., etc., okay? Level 5, or teleoperation if there's no one in the car. Someone needs to be able to take over remotely, right? Level 5, you off. This is the true robot, right? This is the thing that bullshitters tell is going to happen in 2 years. It's not. It is not, right? It's happening beyond the prediction horizon, right? Which is, for Geoff Hinton, 5 years. And that's the guy that invented deep learning, right? So beyond 5 years, even Geoff Hinton doesn't know. I don't know. So level 5, you off, really autonomous. The car goes around, you check your credit card charge, like the XKCD comic, etc., and you're like, what the? All right. And that gives you an idea of the difficulty. It's exponential, right? It's exponential difficulty. This is Emilio Frazzoli, which is a CTO of a startup called Newtonomy. And it's a great course. I really recommend the self-driving car course from MIT, from Lex Friedman. It's a guest lecture in that course. It's available online on YouTube for free. Here it basically talks about the difference between product and service. So autonomous vehicle as a consumer product need to be able to drive everywhere, all the time. The cost needs to go down because it's you and me that are buying it. Global scale, etc., etc. AV as a service, mobility as a service, MaaS, or autonomous, like the Japanese call it, which is weird, but so it's geo, time, weather fenced operation. So you can basically say, you can put the training wheels. You can say, hey, play just in the backyard, right? And just like reduce again the domain of operation. It's also the economics play in a different way in that it's the car is used by other people, et cetera, et cetera, et cetera. So you can put more expensive sensors, et cetera. And basically what he argues, and that I disagree with, is that there's only 2 paths to level 4, okay? And remember level 4, this idea of, the car really drives itself. Might need a human to, help in case, but like not at a given moment's notice. So levels of automation, 1, 2, 3, 4, right? Now, here you have Waymo, Uber, and Autonomy. They start from level 4 in the Google parking lot, and then they gradually Mountain View and the world, right? The evil, so that's the insurgents, right? And the incumbents, the people that are already in the business of making cars and stuff like this, and Tesla, etc. They're like, oh, we start from level 0 because our cars are level 0, and then we upgrade, level up, 1, 2, 3, 4. And as level 3 is very dangerous, as I mentioned before. That's killing people. That's bad. Again, your inner Jon Stewart should be like, well, what about this whole, like the biggest part of the graph here? Like, here, what are you hiding? What is this thing here, right? So obviously, it's more complicated than that. Obviously, this is a straw man. And there's a different way. And that different way, the aviation industry has long since like digested it. So the F-16 and the F-22 is, what they say about the F-16 is that you don't pilot an F-16, the F-16 pilots you. And that's because that plane is unstable. That plane, if all the electronics go off and you let go, normal plane would continue going straight. That plane, poof, all right? And why? That seems like a design flaw. That's one of the most popular fighter jets ever created in existence, right? And so the reason is because it's to enable more maneuverability, to do more complicated maneuvers, you need that instability, because otherwise if you force the stability, you're constraining the system. So they have this notion of relaxed static stability, and they have basically an electronic system that augments the pilot. And when the pilot says, I want to do this thing, like Tom Cruise, and then the plane says, well, if you do that, you're going to die. So I'm going to do slightly, like you meant this, right? And then the plane's going to correct electronically the steering, the command. F-22, even more sophisticated. Drones, obviously, like same thing. So that's why at TRI, and other companies are starting to embrace this. It's not so much about artificial intelligence that does automation, right? Replacement. It's also augmentation has value. Automation has value for sure. Augmentation also has value. So we have one system and 2 modes. One is Chauffeur, the autonomous one, and the other one is Guardian, which is basically augmenting the human driver. It's like it's driving in ghost mode, and then it tells you, hey, you might have not seen this. Then it's maybe nudging you, and then it might actually be taking over. And the beauty is that it's the same stack. It's the same problem, lane change, etc. All the problems are common. And the technology stack, literally the software, is almost the same, except at the 2 ends in terms of the sensors and the UI. But you can use technology in many ways. And this is just an example to show that it's not just automation, there's also augmentation. All right. Safety, really important. I cannot make a presentation about autonomous driving without talking about safety. So very quickly, this is a huge rabbit hole. We're not going to get into this because otherwise we're here till tomorrow morning. And this is already getting late. So there's 2 important concepts that you might want to dig into further later. Again, like I'm going to teach you how to fish. Functional safety, which is about how you minimize risk and have like some kind of automatic fail-safe. Operational design domain. ODD, you might have heard that term floating around in technical press before, etc. So it's just these constraints, right? As I said, like this backyard, etc., etc. So you want to put some constraints like location, weather, etc. And those are requirements, by the way, from NHTSA, right? So you need to provide a safety case. So we don't test on public roads like just for fun, right? There's an entire process, and I won't go into the details. All right, that was the last big part. The other 2 are really short, but so. That part was important, was what are autonomous cars? They're transportation robots, can transport stuff, like carts, like last mile delivery, or trucks. People, shuttles, today. Robotaxis, tomorrow. and cars a little bit in the future and incrementally. And I really want to stress the automation versus augmentation, and safety and the operational design domains are all concepts. This is a super cool XKCD comic. This is probably the most relevant one. I worry about self-driving car safety features. What's to stop someone from painting fake lines on the road, or dropping a cutout of a pedestrian onto a highway to make autonomous cars like swerve and crash? Except those things would also work on human drivers. What's stopping people now? Yeah, causing car crashes isn't hard. I guess it's just that most people aren't murderers. Oh, right, I always forget. An underappreciated component of our road safety system. All the XKCD comics also have the alt text, and you can have a look at them for those of you that don't know. And here it says something like, oh, and if it turns out we all turn into murderers, we'll have to upgrade the firmware or something. All right, who are the players? That's just like high-level overview. There's a lot of players, like huge. I'm not going to go into details. You can check the source and browse and peruse. It's a huge space with, the OEMs, the ride-sharing companies, and then you have all these verticals, et cetera. Sensors, like computing, mapping, safety, and many things. It's a big space. One thing that's important to kind of again understand and learn about the space is obviously high-tech companies are moving into automotive quickly and at scale. So this is a credit from slide from Jim Adler, which is our manager of the Toyota AI Ventures Fund, which is our VC fund that has like 100 million funding, and that we're investing in companies around autonomous driving, robotics, etc. And so he has this really cool slide where he talks about, market share versus time. And you see you have the incumbents like us, like Toyota, right? And so we initially, create cars like 100 years ago, and then we get super mega proficient at making cars and get a lot of money, etc. But eventually we plateau, and then insurgents that start lower than us, right? Then, Tesla, first car, wow, whatever. And then eventually they overcome the incumbents, right? So this is a classical pattern that here in Silicon Valley you all know. You can list companies easily for that. And here, and it's really real in the autonomous driving space, because why? Because the venture capital funding into automotive technology industry is huge. Like it's like 1.34 billion in 2017. It's massive, really massive. And so again, just like thinking out of the box with the augmentation, etc., all the other cases I gave before. Another way to think about the box is that this is a 2D production, actually, of the 3D graph, which is this axis is the known unknowns, and actually the insurgents are optimizing in a different dimension, right? It's like car makers, there's this joke that Toyota is the best manufacturing company in the world. It just turns out that they make cars. And here it's like, oh yeah, we make really good cars. It's about hardware. But then you have the insurgents that say, no, it's about software, and they optimize in a different direction. So the auto industry is basically this strong, stable, we make cars, The insurgents are fast, agile, literally agile, and then obviously that's the hope. We want to be both, right? You want to be Superman. Who doesn't want to Wonder Woman? Strong and stable, fast and agile. So that's really what we're trying to do at TRI. Is like we are these people. Toyota is these people, and we really try to come together and embrace this idea. All right. So the players, in summary, startups, techcos, automakers, suppliers, insurgents versus incumbents. And one thing I haven't talked about that's actually really important is the geographic aspect of this. So US versus China versus EU. There's a lot going on there. Again, too much to say tonight, but China, very, very big in that space. EU, a lot of incumbents that have been really working on that for a long time, like the German example that I gave you earlier, right? Like the Mercedes. And US, obviously, has everything, the insurgents, the incumbents, the startups. Japan too, that's true. That's a good sign, an omission. I should correct that. Japan is there. But honestly, like we are in the US, so a lot of the development for these kind of things is here. So US, Japan, I should have put US/Japan. Thank you, good point. Would you guess this weighs as much as a small adult? What? Probably. Oh, great. Thump. Please fasten your seatbelt. Click. Take me to Anchorage, Alaska. Navigating. Slam. I love self-driving cars. Whose car was that? I don't know, but they shouldn't have left it running. All right, when is X going to happen for any X, for various sets of X? I will cite a French poet, Paul Valéry. L'avenir est comme le reste, il n'est plus ce qu'il était. The future, like everything else, is no longer what it used to be. Okay. You might know this. Prediction is very difficult, especially about the future. So, yes, Americans believe they have invented everything. Turns out it's not. It's Niels Bohr. All right. Okay, self-driving car, grain of salt. I'm not going to make predictions. I'm just going to be basically actually quoting again Lex Friedman, which is this research scientist at MIT, organizing this great course. Carefully differentiate between doubtful, which is promises for future vehicles, which are 2+ years in the future. So anybody telling you stuff that's going to happen 21 and beyond, be doubtful. Skeptical, promises for future vehicles in 1 year or something like this. Possible, the vehicles that are being tested here. But you have to remember that, for instance, like Google in 2009 were already doing like something like 100,000 miles or something like this. It's like really, you know, not because something is happening today at a small scale in a controlled setting that, you know, the road is there, is the end of the road. And real, you know, what, of course, what you can buy today. And Rodney Brooks, which is this legendary robotics professor at MIT, has basically like a very, very nice blog, which I encourage you to read. And basically, his predictions, I have no confidence in my predictions. I have some, but I have no confidence in them. His predictions that he was confident enough to share was 2032, a driverless taxi service in a major US city with arbitrary pickup and drop-off locations, even, you know, in a restricted geographical area. Might be happening, so that definition is fairly lax, might be happening a bit earlier, in my personal opinion. 2045, the majority of US cities have the majority of their downtown under search rules. I'll leave you thinking about that. And that, again, there's an XKCD comic for everything. It's 2011. I want my flying car, dude. You're complaining to me using a phone on which you buy and read books, and which you were using to play a 3D shooter until I interrupted you with what would be a video call if I were wearing a shirt. Can't I have a flying car too? You'd crash it while texting and playing Angry Birds. All right, conclusion, and that's the last slide. Thank you for your patience. It has been a long evening. Autonomous driving. We talked about the why, right, at length at first, because I think it's really important, and this humanitarian values of progress, safety, mobility, economy. How, we talked about the how, so AI, right, and that's the reason I give this talk tonight, hardware, software, and data. Talking about software 2.0, etc. The what. So it's autonomous robots, it's transportation robots that can transport stuff and people, and I talked also about automation and augmentation, right, the two aspects of the same technology, and safety also. And then who, basically tech companies, automakers, mostly, also startups, etc. And when, and make the difference between now, which is roughly 2020, in a few years, 25 or something and beyond, and know that nothing is certain. And that's it. Thank you. And I'm surprised we finished at 9. I had no clue how much time had passed.
Did you want to take questions?
I'm happy to take questions. I can stick around, no problem. So if you have questions that you think is interesting for everybody, I'm happy to answer now, and then of course later. Yes?
You want to comment on the value of maps and things like B2B and B2X, those prerequisites for autonomous driving, or nice to have?
Yeah. So our maps and V2X, so vehicle to infrastructure or vehicle to vehicle communication, a prerequisite, nice to have, etc. So definitely not a prerequisite. My opinion is it's not a prerequisite, and I think that's what most of the leading industry players are thinking. You, at least for V2X, that's for sure. If you rely on infrastructure changing in the US, just look at the state of 101 and you have the answer to your question. Nobody's going to wait. And there are too many opportunities. The field is moving really, really fast. And we can drive as a human. Now we can have software that can learn from humans and all these kind of things. So for V2X, V2I, it's a must. It has to happen. But it is not a prerequisite. So we can deploy, we can have some products, we can do autonomous driving and make it useful and economically useful and saving lives, etc., without it. But the long-term vision, it's undeniable that it's there. Traffic signs and all these kind of things are infrastructure for us to understand. In the future, when humans don't drive anymore, there's going to be infrastructure. It already exists. It's already also in Silicon Valley to some extent, etc. But it's not a prerequisite. Maps is a different problem. Maps, if you have a map, it's really, really useful. And some people say, well, I really want to ship, so I will assume I have a map. I will assume it's always fresh. I will assume it has all the information I need. I will assume I can localize myself against this map. That's a strong assumption that vastly restricts the deployment capabilities of your system, but it has very appealing capabilities in terms of deploying right now. So Waymo, etc., they all make these assumptions, and they restrict the world in which they operate. They restrict their ODD to say if it's unmapped. Like you can buy actually the CT6, Cadillac CT6, which has a Super Cruise system, which can do hands-off, feet off, but not eye off. So and it can only work when it has mapped. It's extremely frustrating because you're driving on a 101 and you're thinking, oh yeah, it works, cool, and then it says like, oh, sorry, you'd have to take over. Wait, what? So it's the maps. It's not fully mapped, etc. We at TRI, we believe map is a very, very useful information that if you have the luxury to have, you have to use, but you need to be robust to its inaccuracy, its lack of freshness, changes that might be there, etc. So you need to use it as an additional source of information that might or might not be trusted. That's the principle we're following. Yes?
When you have cars that are automating the driver, like that Guardian video that you showed where the car swerves out of
Yeah.
an obstacle, how do you think the liability will be divided between the driver and the car company when something goes wrong?
So that's a very good question. So in the case of partial automation or augmentation, what about the liability? How is it split? If the responsibility of driving is like half, like how do you address that? So I'm not an insurance company. I'm not a lawyer, but here, as far as I can tell from today, we have already passed beyond the realm of passive safety. So passive safety is like your seatbelt, your airbags, etc., which is you're going to crash into something. You're crashing into something. How can you save lives when you're crashing, right? Active safety is trying to prevent the crash, right? Which means the car will act on its own in contrast to your decision, right? In opposition to your decision or lack thereof. The lack of a decision is a decision, and you already have this in cars today, right? With automatic emergency braking, like cars that can brake for you, AEB, right? So in that case, it's still the responsibility of the human to drive, but obviously there are laws. I'm not completely entirely familiar with the jargon, but if there's a major flaw in the system, it's the manufacturer's fault. If, as far as I understand it, and if it's a problem of the human, etc., it's like normal car. So it's still a normal car. So how far will this extend, how this will generalize as the cars do more and more, I do not know, and I think nobody can really say because there are different market dynamics, different business models, let's say in insurance, that can revolve around that, and there's no real precedent, I think, because that technology simply does not exist. So I don't know. That's the proper answer, I guess.
Do you have any thoughts on, or has anyone thought about
Yes, so it's called V2V. So when you say V2, when people say V2X, they mean V2I or V2V, vehicle to infrastructure. Like the traffic light would broadcast its state, right? And which is again really important in the future because actually almost all of the accidents that involved AV in California were at intersections, right? And V2V. Is you can imagine that you don't have to detect the cars. They would broadcast their position, their velocity, their driver state. Because one big thing I haven't talked about is actually driver state monitoring. So in Gaidon, in the system, we also have a big element of watching what the driver is doing, where it's looking, is it drowsy, et cetera, et cetera. And so you could imagine the cars broadcasting this. They're like, hey, Joe, my driver is drunk. Oh yeah, okay, I'll be careful. That for sure, is like some of the things you don't need the vehicle to broadcast because you can guess from the outside. Some of the things you cannot. So again, obviously you will need that, but that's much harder because it requires a consensus between automakers on the protocols, and there's also this notion of cybersecurity and all these kind of things. So again, it is something that's active research. It's not something that most people bet on as a prerequisite, and we do not.
Folks, can we give him a big round of applause? So Adrien, thank you very much. Your passion for the subject just came through and through completely. Thank you very much. I like the way you went about the presentation. I mean, you are yourself a PhD in machine learning and have lots of patents and things like that. I was a bit worried, but you got the whole presentation to our level, starting with why we are doing it, what it is, how we are going to go about it, when it is happening, or whatever it is. There's only one request I would like to make. I have a daughter, and she is likely to get her driver's license in the next 4 years. Whatever you do, try to do it within the next 4 years. So I don't have to worry about she getting a driver's license. And that is for your safety, not for her safety, for your safety. So please, whatever you do it within 4 years. And on behalf of Hacker Dojo, we would like to give you this souvenir. And the one thing about this souvenir, it is all made here at Hacker Dojo, in the laser cutting machine lab over here. So on behalf of Hacker Dojo, yeah?
Oh, thank you so much.
Hey folks, thank you very much for all of you for coming over here. It has been like 10 weeks of AI lecture series, sorry. Okay, 10 weeks of AI lecture series going on over here. And many of you, I see many people coming here for many lectures. We really enjoyed you having over here and taking us to all these different technologies of AI and things like that. And we will be having our blockchain series starting in the month of Jan. So thank you very much. Really appreciate that, okay? And, okay.
Just one comment.
Okay, good.
No,
I'm okay, go ahead.
So, yeah, flip right over here. There you go. Guys, thank you very much. My name's Ed Chaudhry. I'm the Executive Director for Hacker Dojo. This is probably the first time you're seeing me up here, but I just want to say thank you to the speakers. Thank you to all the volunteers who helped chip in. Thank you to the viewers online. Sorry for the latency. If I look like a Kung Fu flick where it's a little bit lagged, sorry, we're working on that. Like VS said, we'll be working on that. And Jim, our host here, I want to say thank you to Jim, thank you to VS. We started this in around, June, where we were like, what should we do? Should we have people do workshops? Should this be hands-on? Maybe we could do this in the next iteration. But it's been a lot of hard work, and we're really proud of the results.
I just want to say one thing.
And before you say one thing, Jim, I want to actually, since you and VS are speakers too, you get one, and you get one. Thank you so much, guys. And thanks.
The one thing I wanted to say was that without Ed, this is all Ed's idea, and I just want a big hand for Ed. All right, now we can party.